Hello and welcome. I'm glad you're here. Tonight we're going to explore something vast and intimate all at once: physics. The science of everything, really. The way light moves, the way time bends, the way the universe holds itself together with invisible threads we're only just beginning to understand. But we're not rushing anywhere. There's no test tomorrow, no deadline, no pressure to remember every detail. This is just exploration, a slow drift through ideas that have puzzled and delighted humans for centuries. Maybe you've had a long day. Maybe your mind is still turning over conversations, tasks left undone, things you need to remember tomorrow. That's okay. Let those thoughts be there if they need to be. But for now, for the next little while, you can also let yourself sink into something different, something bigger and stranger and more wonderful than the everyday concerns that fill our waking hours. Physics is, at its heart, the art of paying attention to nature, of asking why and how, and sometimes just what if. It's the study of patterns, of forces, of the way things move and change and stay the same. And tonight, we're going to wander through some of its most beautiful ideas together. Before we begin, I'd love to hear from you. How was your day? What brought you here tonight? Take a moment to write about it in the comments below. I read every one, and there's something special about this little community we're building together. People from all over the world gathering in the quiet hours to wonder about the universe. And if you'd like more of these gentle journeys through science, consider subscribing to the channel. It helps more than you might think, and it means we can keep exploring together. Now, let's begin. Sometimes the simplest facts are the most grounding, aren't they? The word physics, this vast, sometimes intimidating discipline, comes from a Greek word that just means nature, physis, the natural world, the way things are. It reminds us that physics isn't some abstract edifice built entirely in laboratories and blackboards, disconnected from the world we actually live in. It's the opposite. It's the careful, patient study of everything around us. The fall of an apple, the arc of a thrown stone, the way shadows lengthen as the sun moves across the sky. Physics is simply the art of understanding nature, of watching closely and asking questions about what we see. In ancient Greece, the first natural philosophers, people like Aristotle, like Thales, they didn't call themselves physicists. They were simply people curious about the world. They wanted to know why rain falls, why the stars move in patterns, why some materials are solid and others flow like water. They were doing physics before the word even existed in its modern form. They were practicing physis, the study of nature. And in a way, that's what we're all doing when we wonder about the universe. When you look up at the night sky and feel that pull of curiosity, that sense of smallness and connection, you're engaging with physics. You're part of that ancient tradition of simply paying attention to the natural world and letting it fill you with questions. There's something deeply human about that, something that connects us across centuries and cultures, this shared desire to understand the nature of things. Here's something that might make you reconsider every handshake, every hug, every time you've rested your hand on a table. You've never actually touched anything. Not really. Not in the way we usually think of touch. When you press your finger against a surface, let's say the screen of your phone or the pages of a book, what you're feeling isn't contact. it's repulsion. Your atoms and the object's atoms are pushing against each other, never quite meeting. There's an electromagnetic force between them, a kind of invisible cushion created by the electrons in the outer shells of atoms. These electrons repel each other before the atoms can truly touch. You're perpetually hovering above everything you think you're touching, separated by distances so small they're almost meaningless, and yet absolutely real. It's a strange thought, isn't it? That you've spent your entire life floating just above the surface of the world, never quite making contact. Every step you've taken, you've been hovering above the ground. Every object you've held has been suspended in your grasp by forces you can't see or feel directly, only through their effects. And yet, the feeling is real, the sensation of texture, of temperature, of pressure. These are real experiences, even if the mechanism isn't quite what we imagined. Your nerves are responding to those electromagnetic forces, translating them into signals your brain interprets as touch. So in a sense, touch is real. It's just not what we thought it was. It's more like a conversation between force fields than a meeting of surfaces. Perhaps that makes it even more beautiful, this intricate dance of repulsion and response that lets us navigate and experience the physical world, even as we float eternally apart from it. Imagine holding a teaspoon, not a fancy one, just an ordinary teaspoon from your kitchen drawer. Now imagine filling it with material from a neutron star, one of the densest objects in the known universe. That single teaspoon would weigh approximately 6 billion tons. That's roughly the weight of Mount Everest, in a teaspoon. Neutron stars are what remain after certain massive stars die in supernova explosions. The core collapses under its own gravity, and the pressure becomes so extreme that protons and electrons are crushed together to form neutrons. What you end up with is matter compressed to almost unimaginable densities, so dense that a sugar cube-sized amount would outweigh all of humanity combined. The atoms we're familiar with are mostly empty space. If you imagine an atom as a cathedral, the nucleus would be a grain of sand at the center, and the electrons would be tiny specks orbiting near the walls. All that vast emptiness is what gives ordinary matter its volume. But in a neutron star, that emptiness is gone. The matter is packed together so tightly that the entire star, which might contain more mass than our sun, is compressed into a sphere only about 20 kilometers across. A city-sized ball of matter with more mass than the star that gave us light and warmth. Of course, you could never actually hold a teaspoon of neutron star material. Even if you could somehow scoop it up, the gravity would be catastrophic. It would fall through the earth like a stone through mist, dragging everything nearby toward it. But as a thought experiment, it's wonderfully humbling. It reminds us that the universe contains states of matter so extreme they border on the incomprehensible, and yet they follow the same physical laws that govern the fall of rain and the turning of wheels. When you step outside on a sunny day and feel warmth on your skin, you're feeling light that left the sun more than 8 minutes ago. The present moment sun, the one existing right now, in whatever now means across 93 million miles, is unknowable to us. We're always looking at the past. Light travels at about 186,000 miles per second, which seems impossibly fast. And it is fast. Nothing in the universe moves faster. But space is so vast that even at that speed, Light needs time to cross the distances between celestial objects. The sun is roughly 93 million miles away, which means that light, hurtling through the void at maximum cosmic speed, takes 8 minutes and 20 seconds to bridge that gap. This creates a strange situation. If the sun were to suddenly vanish, hypothetically, impossibly, we wouldn't know for more than 8 minutes. The sky would remain bright. The warmth would continue falling on our faces. Everything would seem normal because we'd still be receiving light that left the sun before it disappeared. Only after that 8-minute buffer would darkness arrive, sweeping across the earth as the final photons reached us. It means we never see the sun as it is. We see it as it was. Every sunrise is a memory. Every sunset is history playing out on our retinas. And this isn't unique to the sun. It's true of everything we see. The light from the moon is about 1.3 seconds old when it reaches us. Light from the nearest star beyond our sun, Proxima Centauri, has been traveling for over 4 years. We live in a universe where looking out is also looking back, where distance and time become tangled together in ways that make now a surprisingly complicated concept. If you've ever tried to picture the Big Bang, you might imagine an explosion happening at a specific point in space, with everything rushing outward from that central location. It's a natural image, but it's wrong. The universe has no center. Or perhaps more accurately, every point is the center. Here's a helpful way to think about it. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. If you were an ant standing on one of those dots, you'd see all the other dots receding from you, and you might think, aha, I must be at the center of this expansion. But an ant on any other dot would see exactly the same thing. Every position appears to be the center, because it's not the dots moving through space. It's the space itself expanding. This is what's happening with our universe. Galaxies aren't flying through space away from some central point. Space itself is expanding, carrying the galaxies along with it. Every galaxy sees every other galaxy moving away, and every galaxy can claim to be at the center of that expansion. It's a democracy of perspective. No position is privileged. No location is special. This idea can feel destabilizing at first. We're used to thinking of centers, of fixed reference points. But the universe operates on different principles. It's homogeneous and isotropic, which is a technical way of saying it looks roughly the same in all directions from any point. There's no cosmic address that marks the spot where it all began because the Big Bang didn't happen at a location. It happened everywhere, simultaneously. All of space was concentrated into an infinitely dense point, and when expansion began, every point in our current universe was there. The Big Bang happened here, where you are right now, and also 13 billion light years away in every direction. Perhaps that's the most egalitarian thing about the cosmos. We're all at the center of everything. The model of the atom you might remember from school, the one with electrons circling the nucleus like tiny planets around a sun, is beautifully wrong. It's a useful fiction, a stepping stone toward understanding, but it's not how atoms actually work. Electrons don't orbit. They don't follow neat circular or elliptical paths. Instead, they exist in what we call orbitals, which are really probability clouds. An electron in an atom is simultaneously everywhere it could possibly be within that cloud. spread out like a mist or a whisper, until something interacts with it and forces it to choose a specific location. This is one of the strangest features of quantum mechanics. At the quantum level, particles don't have definite positions and velocities the way objects do in our everyday world. An electron doesn't have a location. It has a probability distribution. If you were to measure where the electron is, you'd find it at a specific point, but before that measurement, it was smeared across all possible positions, existing in a superposition of states. It's as if the electron refuses to commit. It keeps its options open, inhabiting multiple possibilities at once, until observation collapses those possibilities into a single reality. And even then, if you measure again a moment later, you might find it somewhere else within the cloud, because the wave function spreads out again immediately after measurement. Some people find this unsettling. It challenges our intuitive sense of how things should behave. Objects should be in one place at one time, shouldn't they? But electrons and all quantum particles don't follow the rules we've learned from our macroscopic experience. They follow quantum rules, which are beautifully, maddeningly different. And perhaps there's something freeing about that. The universe at its smallest scales is fuzzy, probabilistic, irreducibly uncertain. Maybe the universe is content being undecided, existing in gentle superposition, until the moment it absolutely must choose. Here's something that sounds like it shouldn't be true. Sometimes hot water freezes faster than cold water. It's called the Mpemba effect, named after a Tanzanian student named Erasto Mpemba, who noticed this while making ice cream in the 1960s. He observed that hot ice cream mix froze faster than cold mix, and when he asked his teacher about it, the teacher dismissed it as impossible. But Mpemba persisted, and eventually his observation was confirmed. The phenomenon had been noticed before. Aristotle mentioned it. Francis Bacon wrote about it. But it was Mpemba's careful documentation that brought it to modern scientific attention. And despite being known for decades, centuries really, scientists still debate exactly why it happens. Several factors might contribute. Hot water evaporates more quickly, reducing the total mass that needs to freeze. The temperature difference between hot water and its environment is greater, which might enhance heat transfer. Hot water might have different patterns of convection that help distribute heat. Dissolved gases behave differently at different temperatures. Perhaps it's some combination of all these factors, varying depending on specific conditions. What's wonderful about the Mpemba effect is that it reminds us how much we still don't fully understand, even about something as everyday as water freezing. It's a humbling thought. We can send spacecraft to the edge of the solar system. We can detect gravitational waves from colliding black holes. And yet a pot of water on a stove can still surprise us with behavior we can't completely explain. Maybe that's okay. Maybe it's good to be reminded that nature still holds surprises, that even familiar phenomena can harbor mysteries. The universe doesn't owe us easy answers, and perhaps the questions that linger longest, the ones that resist simple explanation, are the ones that keep us curious, keep us wondering, keep us paying attention. Take a standard deck of 52 playing cards. Shuffle it thoroughly. Congratulations! You've almost certainly created an arrangement that has never existed before in the entire history of card playing, and will never exist again. The number of possible arrangements of 52 cards is 52 factorial, written as 52, which means 52x 51x 50x 49, all the way down to 1. That number is incomprehensibly large, approximately 8x 1067. To put that in perspective, there are estimated to be about 1050 atoms on Earth. The number of possible card arrangements is a trillion times larger than that. It's a bit like rolling 100 dice and finding all the same number, except the odds are far, far worse. If every person who ever lived shuffled a deck of cards every second for their entire lives, and this continued for billions of years, we wouldn't even begin to scratch the surface of all possible arrangements. This astronomical number emerges from something simple: permutations. Each card you place has fewer options than the one before. The first card can be any of 52. The second can be any of the remaining 51. The third, any of 50, and so on. These choices multiply together, and the result explodes into numbers that dwarf our everyday experience. There's something both wonderful and melancholy about this. Every shuffle is unique, unrepeatable, a singular moment in the universe's history. But also, it means that any particular arrangement you're hoping for, say, a perfect sequence from ace to king in all 4 suits, is so unlikely you could shuffle for longer than the universe has existed and never see it. Randomness contains both infinite possibility and infinite improbability, and perhaps that's a good metaphor for existence itself. Vast potential, most of it forever unrealized, and the beauty of the specific moment we happen to occupy. When scientists talk about the speed of light, they don't say approximately or around. They say exactly 299,792,458 meters per second, not 299,792,457, not 299,792,459. That precise number, with complete certainty. But here's the twist. This isn't because we've measured light speed with perfect precision. It's because we've redefined the meter to make it exact. In 1983, the international scientific community decided to fix the speed of light at that specific value, and then define the meter based on it. A meter is now defined as the distance light travels in 1/209,792,458 of a second. It's a bit like deciding that instead of measuring how long a day is, we'll define a day as exactly 24 hours and then adjust our measurements accordingly. We turn the speed of light from something we measure into something we use to measure other things. Why do this? Because the speed of light is constant. It's the same in all reference frames, under all conditions, everywhere in the universe. It's one of the most fundamental constants in physics, built into the very fabric of space-time itself. It made sense to anchor our system of measurement to it, rather than to some arbitrary physical object, like the platinum bar in Paris that used to define the meter. This decision reflects something profound about how science works. We don't just discover facts about the universe, we also construct frameworks for understanding those facts. We choose our reference points, our standards, our ways of organizing knowledge. And when we find something truly fundamental, like the speed of light, we build our entire system of measurement around it. In a sense, the meter is just light's speed divided into convenient chunks. Every time you measure a distance, you're invoking the cosmic speed limit, that ultimate velocity beyond which nothing in the universe can go. Imagine you're underwater in a swimming pool and someone claps their hands above the surface. You'd hear it, but you might also notice something strange if you were paying close attention. Sound behaves differently underwater. It moves faster, about 4 times faster, in fact. In air, sound travels at roughly 343 meters per second at room temperature. It's a speed we're all familiar with, even if we don't think about it. The reason you see lightning before you hear thunder, the delay between a distant firework and its boom. But in water, sound rockets along at about 1,480 meters per second. The denser medium actually conducts sound more efficiently because the molecules are closer together, allowing vibrations to transfer more quickly from one to the next. This is why whales can communicate across entire ocean basins. A blue whale's low-frequency call can travel for hundreds of miles underwater, the sound waves propagating through the ocean's depths with remarkable efficiency. What would be impossible in air, conversing with someone on another continent using only sound, becomes feasible in the ocean's dense, dark expanse. There's something poetic about that, isn't there? The ocean is a communication superhighway for sound, a medium where voices can carry farther than anywhere on land. Whales evolved to exploit this, developing songs of such complexity and beauty that they can last for hours, carrying messages we still don't fully understand across distances that dwarf our own unaided vocal range. It reminds us that the properties of the medium matter as much as the message. Sound isn't just sound, it's a vibration that depends entirely on what it's moving through, changing speed and character as it transitions from air to water to solid materials. The Eiffel Tower is not a fixed thing. It breathes with the seasons, expanding and contracting as temperatures rise and fall. In the heat of a Parisian summer, the iron structure can grow up to 6 inches taller than it stands in winter's cold. This happens because of thermal expansion, a fundamental property of matter. When you heat most materials, their atoms vibrate more vigorously, pushing against each other and taking up more space. The effect is usually tiny, imperceptible in everyday objects, but the Eiffel Tower is massive, constructed from over 18,000 individual iron pieces. When summer sun bakes that metal, all those microscopic expansions add up. The tower literally stretches toward the sky on warm days, then settles back down when temperatures drop. It's a slow, graceful dance with the seasons, invisible unless you're measuring carefully. Engineers who designed it knew this would happen. They built in flexibility, allowing the structure to expand and contract without damaging itself. The iron lattice can breathe. There's something wonderfully humbling about this. We think of monuments as permanent, unchanging, especially something as iconic as the Eiffel Tower. But even our grandest structures are subject to the same physical laws as everything else. The tower is made of atoms, and atoms respond to temperature. No human construction transcends physics. We work within its constraints, building things that can flex and adapt, because rigidity in the face of natural forces is a recipe for failure. And maybe there's a lesson there about impermanence, about the way everything, even iron towers that seem eternal, is constantly changing, responding to its environment, never quite the same from one moment to the next. The Eiffel Tower grows and shrinks. The world turns. Nothing stays still. Here's a strange fact about your own body. You're taller when you wake up than when you go to bed, by about half an inch, maybe a little more. Throughout the day, gravity compresses the cartilage in your spine, squeezing the discs between your vertebrae like sponges under weight. By evening, you're measurably shorter. Then, while you sleep, lying horizontal, the pressure releases. Your spine decompresses. Fluid flows back into those cartilage discs, plumping them up again. By morning, you've regained that lost height. You wake up slightly taller, ready to be compressed again by another day of standing and sitting and walking. It's a daily cycle you've probably never noticed. Unless you were measuring yourself carefully at different times of day, there'd be no reason to. Half an inch isn't enough to see in the mirror or feel in your clothes, but it's there, a small reminder that your body is constantly responding to forces, gravity chief among them. Astronauts experience a more extreme version of this. In the microgravity of space, without the constant downward pull of Earth, their spines elongate. They can grow 2 or 3 inches taller during long missions. It sounds appealing until you consider that this also causes back pain and other complications. Our bodies evolved in Earth's gravity. Remove it, and strange things happen. But for those of us on Earth, the daily compression and expansion of our spines is just another rhythm, like breathing or heartbeat. Our bodies exist in time, changing subtly but constantly. You are not exactly the same height all day. You are not exactly the same person, molecule by molecule, that you were yesterday. The atoms that make up your body are constantly being replaced. You're a pattern maintained through change, a process rather than a thing. And perhaps that's true of everything, really. Nothing is static. Everything flows. Light is strange. A photon, a single particle of light, can travel for billions of years, crossing vast cosmic distances, and from its own perspective, no time passes at all. Departure and arrival are simultaneous. This is one of the bizarre consequences of special relativity. As you approach the speed of light, time slows down relative to stationary observers. And for something moving at exactly the speed of light, time stops completely. A photon experiences no duration. It leaves a distant star and arrives at your eye in what is, from the photon's perspective, a single instant with no interval between. It's difficult to wrap your mind around. We experience time as a flow, a sequence of moments, but a photon doesn't. It exists in an eternal present, untouched by the passage of time. It doesn't age. It doesn't change. It simply is, spanning billions of light years and billions of years in a single, timeless moment. What does this mean? It means that when you look up at a star that's, say, 10 billion light years away, you're seeing light that left that star 10 billion years ago, when the universe was much younger. But to the photon that traveled that distance, no time elapsed. The entire journey was instantaneous. It creates a strange duality. From our perspective, light takes time to travel. We measure its speed, calculate how long it takes to cross distances. But from light's perspective, if we can even speak of such a thing, there is no journey. There is only existence, timeless and unchanging. Perhaps this is the universe's way of reminding us that time itself is relative, not absolute. It depends on your frame of reference, your velocity, your position in a gravitational field. There is no universal clock ticking away in the background. Time is local, personal, woven into the fabric of space-time in ways that make now a surprisingly slippery concept. The Earth has a magnetic field generated by the churning of molten iron in its outer core, and this field has poles, just like a bar magnet. Right now, your compass needle points toward the magnetic North Pole, but this hasn't always been the case. and it won't always be in the future. The Earth's magnetic poles have reversed many times throughout geological history. North becomes south, south becomes north. These reversals happen irregularly, roughly every 200,000 to 300,000 years on average, though the intervals vary wildly. The last reversal occurred about 780,000 years ago, which means we're arguably overdue for another one. We know this happened because when volcanic rock solidifies, iron-rich minerals within it align with the Earth's magnetic field at that moment, essentially creating a frozen record of the field's direction. By studying ancient lava flows and sediment layers, scientists have reconstructed the history of these reversals, finding a pattern of flips stretching back millions of years. What triggers a reversal? We don't fully know. The Earth's magnetic field is generated by complex flows of liquid metal deep beneath our feet, a geodynamo driven by heat and rotation. These flows can become chaotic, and occasionally they reorganize themselves in a way that flips the field. The process isn't instantaneous. It can take thousands of years, during which the field weakens and becomes more complex, sometimes developing multiple poles before settling into a new configuration. Should we worry? Probably not imminently. The magnetic field shields us from solar wind and cosmic radiation, so a weakened field during reversal could potentially increase radiation exposure. But life has survived many reversals before, and there's no evidence of mass extinctions linked to them. Still, it's a reminder that even the most fundamental features of our planet, things that seem permanent and stable, are actually dynamic, changing on timescales that dwarf human history but are mere moments in the Earth's long life. Every rainbow you've ever seen has been incomplete. What appears as an arch in the sky is actually a full circle, but the ground blocks the bottom half from your view. The geometry of a rainbow is fixed. When sunlight enters a water droplet, it refracts, bends, reflects off the back of the droplet, and refracts again as it exits. This process separates white light into its component colors. The angle at which this light reaches your eye is always about 42 degrees from the antisolar point, the point directly opposite the sun from your perspective. That 42-degree angle forms a cone of light around the antisolar point. If you're standing on the ground, you see the upper part of that cone as an arch against the sky. But from an airplane, or from the top of a mountain with the right conditions, you can see more of the circle. Some pilots regularly see full circle rainbows, or nearly complete ones, because there's no ground to block their view. There's something delightful about this. It means that the familiar arch we all recognize is just a fragment, a partial view of a more complete phenomenon. The full geometry exists whether we can see it or not. The rainbow doesn't care about the ground blocking our view. It forms its complete circle regardless. It's a good metaphor, perhaps, for how we perceive many things. We see parts, fragments, and we extrapolate the whole. Sometimes we're right. Sometimes there's more to the picture than we realize. The universe is full of circles we only see as arches, patterns we only glimpse partially, phenomena we understand incompletely. And that's okay. We work with what we can observe. We build models. We piece together understanding from fragmentary evidence. And occasionally, we get to step up into an airplane and see the whole circle, and marvel that it was there all along. Lightning is raw power made visible, a violent, brilliant discharge of electricity that lasts only a fraction of a second. And yet, if you could somehow capture and store the energy in a single lightning bolt, it could power a 100-watt light bulb for more than 3 months. A typical lightning bolt carries about 1 billion joules of energy. That's a staggering amount, delivered in roughly 1/5 of a second. The current can reach 30,000 amperes. The temperature in the channel can exceed 30,000 Kelvin, 5 times hotter than the surface of the sun. The air around the bolt expands so violently it creates the thunder we hear rolling across the sky. And yet, despite this tremendous energy, most of it dissipates as heat and light and sound. The bolt doesn't deliver its energy to a useful load. It just tears through the air, balancing the electrical potential between clouds and ground. If we could capture it efficiently, that energy could indeed power devices for months. But in practice, lightning is too brief, too unpredictable, too violent to harness effectively. We have the technology to capture some energy from lightning, but the engineering challenges and economics make it impractical compared to other energy sources. Still, there's something awe-inspiring about the sheer power involved. Nature generates these million-volt discharges thousands of times per second around the world. The atmosphere is alive with electrical potential, constantly building and releasing, balancing charges between earth and sky. And we're just small creatures moving beneath this vast electrical dance, occasionally startled by its violence, reminded that the air itself contains tremendous energy, waiting for the right conditions to unleash it in a blinding flash. You've probably heard the claim that old windows are thicker at the bottom because glass is a liquid that slowly flows downward over centuries. It's a charming idea, and it speaks to something true about glass, even if the window explanation is wrong. Glass is what we call an amorphous solid. Unlike crystalline solids, where atoms are arranged in regular, repeating patterns, glass has a disordered structure more like a liquid. When you cool molten glass, it becomes more viscous, thicker, slower moving, but it doesn't undergo the sharp phase transition that water does when it freezes into ice. Instead, it just gets slower and slower until it's essentially solid for all practical purposes, but without ever forming a crystal lattice. So is it a liquid or a solid? In some sense, it's both, or neither. It's a liquid that's so viscous it behaves like a solid on human timescales. At room temperature, glass would take billions of years to flow appreciably. So while it's technically true that glass lacks a crystalline structure and retains some liquid-like properties, it's not flowing in your windows. The thickness variation in old glass panes comes from the manufacturing process. They simply weren't made uniform, but the deeper point remains. The distinction between solid and liquid isn't always as clear-cut as we might think. There are states of matter that blur the boundaries, that refuse to fit neatly into our categories. Glass is one. Others include gels, colloids, plasmas, liquid crystals. The universe is full of in-between states, things that are sort of one thing and sort of another, depending on how you look at them and what time scale you're considering. Maybe that's true beyond physics too. Maybe most interesting things exist in the borderlands, between categories, refusing to be neatly classified. There's a bottom to temperature, a point beyond which you cannot go, no matter how sophisticated your refrigeration. We call it absolute zero, 273.15 degrees Celsius, or 0 Kelvin. At this temperature, atoms would reach their minimum possible energy state, vibrating as little as quantum mechanics allows. Notice the careful phrasing, almost entirely. Even at absolute zero, atoms don't stop moving completely. Quantum mechanics forbids it. The Heisenberg uncertainty principle means that if you knew an atom's position perfectly, you'd know nothing about its momentum, and vice versa. For an atom to be completely still, you'd need to know both position and momentum exactly, which is impossible. So even at absolute zero, there's a baseline quantum jitter, a zero-point energy that can never be removed. We've come extraordinarily close to reaching absolute zero in laboratories. Scientists have cooled atoms to within a billionth of a degree, creating states of matter like Bose-Einstein condensates, where quantum effects become visible at macroscopic scales. But reaching exactly zero is impossible, not just technologically difficult, but fundamentally prohibited by the laws of thermodynamics and quantum mechanics. There's something philosophically interesting about this hard limit. Temperature measures the average kinetic energy of particles. You can always add more energy. There's no upper limit to how hot something can get. But there is a lower limit. You can't have less than zero energy. You can't be colder than completely still, or as still as quantum mechanics allows. It's an asymmetry in the universe, a boundary built into the nature of energy and motion. And perhaps there's comfort in that. In a universe that can seem infinite and unbounded, it's oddly reassuring that there's at least one absolute reference point, one temperature that represents a true zero, a foundation below which nothing can fall. Right now, as you lie here listening, your body is glowing. Not metaphorically, actually glowing, emitting electromagnetic radiation into the space around you. You're a light source, a lamp of sorts, radiating energy constantly. The light you emit is infrared, wavelengths longer than visible light, invisible to the human eye but detectable by thermal cameras. All objects with temperature above absolute zero emit thermal radiation, and the wavelengths depend on the temperature. Your body, at roughly 37 degrees C, emits most strongly in the infrared portion of the spectrum. If you could see in infrared, you'd see yourself and everyone around you shining, glowing with the heat of metabolism. You'd see the warm spots and cool spots on your body, the patterns of blood flow, the energy radiating from your skin. Thermal cameras reveal this hidden light, showing a world that's constantly luminous with invisible radiation. This isn't some special property unique to living things. Everything glows. Your refrigerator glows. The walls of your room glow. Even ice cubes glow, though more dimly. It's all black body radiation, a fundamental consequence of having temperature. The hotter something is, the shorter the wavelengths it emits, and the brighter it glows. The sun glows in visible light because it's so hot. You glow in infrared because you're much cooler. But the principle is the same. You're participating in one of the universe's most fundamental processes, the conversion of thermal energy into electromagnetic radiation, the constant exchange of photons between all objects, the way heat spreads and equilibrates through space. You are a star in your own small way, a gentle infrared star radiating your warmth into the world, connected to everything around you through this exchange of light. You are made of stardust. It's become a cliché, repeated so often it's lost some of its power. But it's also literally beautifully true. Every atom of carbon, nitrogen, oxygen, iron in your body, every element heavier than hydrogen and helium, was created inside stars. The Big Bang produced mostly hydrogen and helium, the lightest elements. Everything else had to be built up through nuclear fusion, and that requires the tremendous heat and pressure inside stellar cores. For billions of years, stars have been fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon and oxygen, and in the cores of massive stars, the process continues all the way up to iron. But there's a limit. Iron is the most stable nucleus. Fusing iron requires energy rather than releasing it. So once a star's core becomes iron, fusion stops. For massive stars, this triggers catastrophic collapse, a supernova, which releases enough energy to forge even heavier elements and scatter them into space. The cloud of gas and dust from which our solar system formed was enriched by countless previous generations of stars. They lived, died, and exploded, seeding the cosmos with heavy elements. Those elements coalesced into planets, rocks, oceans, and eventually, living things. The calcium in your bones was forged in a stellar furnace. The iron in your blood was created in the violent death throes of a massive star. It means you're not separate from the universe. You're a temporary arrangement of matter that has cycled through stars, through space, through planets, and now briefly takes the form of a conscious being. You are the universe looking at itself, made of atoms that have existed for billions of years and will continue to exist long after you're gone, cycling endlessly through new forms. There's a deep continuity there, a connection to everything that has been and will be. You are ancient and you are temporary, and perhaps both of those things are equally true. Imagine pouring liquid helium into a cup and cooling it below 271 degrees Celsius. Something extraordinary happens. The helium becomes a superfluid, a state of matter so strange it seems to violate common sense. Superfluids have zero viscosity, no friction, no resistance to flow whatsoever, and this creates behavior that looks almost supernatural. A superfluid can flow up and over the walls of its container, defying gravity, creeping along surfaces in a thin film until it drips out the bottom and escapes. If you set the container spinning, the superfluid will continue rotating forever, or at least until it warms up enough to return to normal liquid behavior. This happens because at such extreme cold, the helium atoms enter a quantum state where they all share the same wave function. They move in perfect coordination, as if they're one single entity rather than individual particles. Normally, atoms in a liquid collide and jostle, creating friction. But in a superfluid, the quantum coherence means atoms can't scatter off each other in the usual way. They flow without resistance. It's one of the most striking examples of quantum mechanics becoming visible at macroscopic scales. Usually, quantum effects are confined to individual atoms and subatomic particles, too small to see directly. But superfluids bring quantum weirdness into the realm of things you can pour and observe, creating behavior that seems impossible. There's something unsettling and beautiful about watching a superfluid climb walls. It reminds us that matter, at extreme conditions, doesn't follow the rules we've learned from everyday experience. The universe contains states where liquid flows upward, where friction vanishes, where the quantum and the macroscopic merge in ways that challenge our intuitions about what should be possible. Here's a strange fact. Your feet are aging slightly slower than your head. The difference is minuscule, fractions of a nanosecond over a lifetime. but it's real. Your feet are deeper in Earth's gravitational field, and time runs slower there. This is gravitational time dilation, predicted by Einstein's general relativity and confirmed by precise atomic clocks. Gravity doesn't just pull on matter, it warps time itself. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. The effect becomes dramatic near massive objects. A clock near the surface of a neutron star would tick thousands of times slower than one in empty space. Near a black hole's event horizon, time dilation becomes extreme. If you could watch someone falling toward the event horizon from a safe distance, you'd see them slow down, their movements becoming more and more sluggish as they approach, asymptotically freezing as they cross the boundary, though from their perspective, they'd fall through in finite time. This isn't some abstract theoretical curiosity. GPS satellites have to account for gravitational time dilation to function accurately. They orbit about 20,000 kilometers above Earth, where gravity is weaker and time runs slightly faster than on the surface. Without correcting for this, along with the velocity-based time dilation from special relativity, GPS coordinates would drift by kilometers each day. It means time isn't a universal constant ticking away uniformly everywhere. It's local, relative, woven into the geometry of space-time. Your head exists in a slightly different temporal flow than your feet. The universe is full of different rates of time, all valid, all real, all depending on where you are in the gravitational landscape of space. Einstein called it spooky action at a distance, and he wasn't comfortable with it. Quantum entanglement suggests that two particles can be connected in such a way that measuring one instantly affects the other, regardless of the distance between them. You could separate them by the width of the universe, and they'd still remain correlated. Here's how it works. When two particles become entangled through various quantum processes, their properties become linked. If you measure one particle's spin and find it pointing up, you'll instantly know the other is pointing down, even if it's light years away. The measurement of one seems to instantaneously determine the state of the other. But, and this is crucial, you can't use this to transmit information faster than light. The results of your measurement are random until you make them. You can't control what you'll find. Only afterward, when you compare notes with someone measuring the other particle, do you discover the correlation. So while the particles are connected in this strange, non-local way, causality remains intact. What does it mean? That's still debated. Some interpretations suggest the particles share a single quantum state, regardless of distance. Others propose hidden variables we haven't discovered. Still others embrace the weirdness, accepting that nature is fundamentally non-local at the quantum level. Experiments have confirmed entanglement repeatedly. It's not speculation, it's observable reality, and it's being used practically now in quantum cryptography and quantum computing. The universe permits these strange correlations, these instant connections across space, while still preserving the cosmic speed limit. It's as if nature found a way to be both intimately connected and causally restricted, allowing for quantum weirdness while preventing paradoxes. This sounds backward, doesn't it? Glass is brittle, rubber is bouncy. Surely a rubber ball bounces better. But if you made two perfect spheres, one of solid glass, one of solid rubber, and dropped them from the same height onto a hard surface, the glass ball would bounce higher. The reason is elasticity, which is slightly different from how we use the word colloquially. In physics, elasticity measures how well a material returns to its original shape after being deformed. Glass is actually more elastic than rubber in this technical sense. When the glass ball hits the ground, it deforms slightly, stores that energy, and releases it very efficiently, converting it back into upward motion. Very little energy is lost to heat. Rubber, despite feeling bouncy, actually absorbs more energy. It deforms more dramatically. And internal friction as it squishes and rebounds converts kinetic energy into heat. Some of that energy is lost, so the bounce isn't as high. Of course, there's a catch. While glass bounces higher, it's also far more likely to shatter. Its brittleness means it can't handle the stress of impact as well as rubber can. Rubber is tougher, better at absorbing energy without breaking, even if that means bouncing less efficiently. It's a nice reminder that properties we think we understand often have nuances. Bouncy and elastic aren't quite the same thing. The universe makes distinctions we overlook in casual speech. Glass can bounce better than rubber, even as it remains fragile in ways rubber isn't. Materials have multiple properties, and excellence in one doesn't guarantee excellence in another. Honey is nearly immortal. Archaeologists excavating ancient Egyptian tombs have found pots of honey thousands of years old, sealed and forgotten. And when they open those pots, the honey inside is still perfectly edible. 3,000 years later, it hasn't spoiled. What makes honey so stable? Several factors working together. First, it's extremely low in water content, usually around 17%. Bacteria and microorganisms need water to grow, and honey simply doesn't provide enough. It's too dry, too concentrated to support microbial life. Second, honey is acidic, with a pH typically between 3 and 4.5. Most bacteria prefer more neutral environments. The acidity creates an inhospitable environment where few organisms can thrive. Third, bees add an enzyme called glucose oxidase to honey. This enzyme produces small amounts of hydrogen peroxide, a natural antimicrobial agent. It's a defense mechanism the bees have evolved to protect their food stores, and it works remarkably well. And finally, honey's high sugar concentration creates osmotic pressure that draws water out of any bacterial cells that do attempt to grow, essentially desiccating them before they can multiply. All these factors combine to create a substance that's effectively imperishable under the right conditions. Sealed and stored properly, honey can last indefinitely. It may crystallize over time, becoming grainy, but that's just a physical change, not spoilage. Gentle heating will return it to liquid form. There's something almost mythical about this permanence. In a world where nearly everything decays, where preservation requires constant effort, honey just exists, unchanging, sweetness preserved through centuries. Perhaps that's why ancient cultures considered it sacred, a gift from the divine. It seemed to transcend time itself. There's a persistent myth that water draining from your sink or toilet swirls clockwise in the northern hemisphere and counterclockwise in the southern due to the Coriolis effect. It's a lovely idea, connecting your bathroom plumbing to the rotation of the earth. Unfortunately, it's wrong. The Coriolis effect is real. It's the apparent deflection of moving objects caused by Earth's rotation. Air masses and ocean currents are definitely affected by it, which is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern. But the Coriolis force is extremely weak at small scales. Your sink is just too small for it to matter. What actually determines which way water swirls in your drain is the shape of the basin, the angle you poured the water, residual currents in the liquid, and countless other local factors that dwarf the minuscule Coriolis effect. You can make water drain in either direction in either hemisphere just by introducing a slight rotation when you fill the basin. However, with very carefully controlled experiments, perfectly symmetrical basins, water left to settle for days to eliminate all other currents, extremely sensitive measurements, scientists have detected the Coriolis effect in draining water, but it requires laboratory precision. In your bathroom, it's irrelevant. It's a good reminder that just because a force exists doesn't mean it dominates every situation. The universe contains many forces, many effects, and which ones matter depends on scale and context. The Coriolis force shapes hurricanes, but not your toilet. Gravity holds galaxies together, but loses to electromagnetic forces at atomic scales. Every physical phenomenon has its domain, its range of relevance, beyond which other factors take over. Diamond is the hardest natural material on Earth. It's also a symbol of permanence, forever, unbreakable bonds. And yet, diamond will burn. Given enough heat and oxygen, a diamond will combust, vanishing into carbon dioxide gas, leaving nothing behind. This seems shocking until you remember what diamond actually is: carbon. The same element that makes up coal, graphite, the charcoal in your grill. What makes diamond special is its structure. Carbon atoms bonded in a rigid, three-dimensional lattice that gives it extraordinary hardness. But chemically, it's still carbon. And carbon, when heated in the presence of oxygen, will oxidize. It will burn. The ignition temperature is high, around 800 degrees Celsius in pure oxygen, higher in air, but it's achievable. If you put a diamond in a furnace with sufficient oxygen, it will burn like any other carbon-based material, producing carbon dioxide and disappearing completely. There are documented cases of diamonds burning in house fires, leaving only the metal settings behind. Insurance investigators occasionally have to explain to distraught owners that yes, diamonds can burn, and no, the fire wasn't impossibly hot, it was just hot enough. It's a humbling reminder that hardness isn't the same as stability or indestructibility. Diamond resists scratching and crushing beautifully, but it has no special protection against chemical reactions. In the right conditions, the hardest substance can vanish like smoke. Perhaps there's a metaphor there. The things that seem most permanent, most unbreakable, often have unexpected vulnerabilities. Strength in one dimension doesn't guarantee invulnerability in all others. Everything, even diamonds, exists in a delicate balance with its environment, stable only within certain conditions, fragile in ways that aren't immediately obvious. When you put food in a microwave oven, you're not heating it with heat exactly. You're bombarding it with electromagnetic radiation at a frequency specifically chosen to make water molecules spin. Water molecules are polar. One end is slightly positive, the other slightly negative. When microwaves pass through food, their oscillating electromagnetic field causes these polar molecules to rotate, trying to align with the field. But the field is oscillating at 2.45 billion times per second, so the molecules keep flipping back and forth, spinning frantically. This molecular rotation creates friction. The water molecules jostle against their neighbors, and that friction converts electromagnetic energy into heat. The water heats up, and that heat spreads to the surrounding food. It's why microwave ovens are so effective at heating wet food, but terrible at heating dry food. No water means no polar molecules to spin, means no friction, means no heat. A bone-dry plate will stay cool in a microwave, while the moist food on top of it gets hot. It's also why microwave heating can be uneven. The waves don't penetrate uniformly, and areas with more water heat faster. The rotating turntable is an attempt to even things out by exposing different parts of your food to the wave patterns, but it's imperfect. There's something elegant about this method of heating. Rather than using conduction or convection, contact with hot surfaces or fluids, microwaves reach directly into the food and agitate its molecules. It's heating from the inside out, targeting the water wherever it happens to be. A strange, modern way to cook, turning electromagnetic fields into dinner through the dance of polar molecules. The word laser has become so common we forget it's an acronym. Light amplification by stimulated emission of radiation. Each word describes part of how this remarkable device works. Ordinary light, from the sun, from a light bulb, consists of photons traveling in random directions with random phases. The light waves are incoherent, jumbled together, but laser light is different. All the photons march in lockstep, their waves perfectly synchronized, traveling in the same direction with the same wavelength and phase. This coherence gives lasers their extraordinary properties. Because the light waves reinforce each other. Rather than interfering randomly, lasers can be focused to incredibly small points. They can travel long distances without spreading much. They can carry enormous amounts of energy in a tight, controlled beam. The process involves exciting atoms to higher energy states, then triggering them to release that energy as photons in a coordinated way. One photon stimulates another atom to emit a photon identical to the first. Same wavelength, same phase, same direction. This photon stimulates another and another, cascading through the material until you have a coherent beam of synchronized light. Lasers have become ubiquitous. They read barcodes, play music from CDs, perform surgery, cut metal, measure distances to the moon, transmit data through fiber optic cables. A technology that seemed exotic decades ago is now everywhere, doing countless tasks. And it all comes down to making light orderly, getting photons to cooperate, to move together rather than randomly. In a universe that tends toward disorder, lasers are small victories for coherence and organization. How does a plane stay in the air? The answer involves Bernoulli's principle, which states that faster moving fluid creates lower pressure. A plane's wing is shaped to make air move faster over the top than the bottom, creating a pressure difference that generates lift. The wing's curved upper surface forces air to travel a longer path than the air moving along the flatter bottom. To cover more distance in the same time, the air on top must move faster. According to Bernoulli, this faster-moving air has lower pressure. The higher pressure air below pushes upward, and the wing and the plane attached to it rises. It's not the complete explanation. There are additional factors. The wing's angle of attack, the deflection of air downward, creating an equal and opposite upward force, Newton's third law, circulation around the wing. Aerodynamics is complex, But Bernoulli's principle is a crucial part of understanding why wings generate lift. What's remarkable is that this same principle appears everywhere. It explains why shower curtains get sucked inward when you turn on the water. The fast-moving stream creates low pressure. It's why prairie dog burrows have multiple entrances. Wind blowing over one creates low pressure that draws the air through the tunnel. It's why atomizers and carburetors work, why ventilation systems function, why sailboats can sail faster than the wind pushing them. Faster fluid, lower pressure. It's a simple relationship with profound consequences, allowing machines heavier than air to soar, enabling technologies from spray bottles to HVAC systems. The universe follows consistent rules, and once you understand one of them, you see it everywhere, explaining phenomena that seem unrelated until you recognize the common principle beneath them. If you could travel at near light speed, the universe would become strange. Time for you would continue normally, your heartbeat. Your thoughts, your experience of duration would feel unchanged. But if you looked back at Earth, you'd see something remarkable. Clocks ticking slower, people moving like they're underwater, everything grinding toward stillness. This is time dilation, one of the most counterintuitive predictions of special relativity. The faster you move relative to something else, the slower time passes for them from your perspective, and vice versa. It's reciprocal and real, confirmed by countless experiments. Astronauts on the International Space Station experience this, though the effect is tiny. They orbit at about 28,000 kilometers per hour, fast enough that time runs slightly slower for them than for people on Earth. After 6 months in space, an astronaut has aged about 0.007 seconds less than if they'd stayed on the ground. It's negligible but measurable with precise atomic clocks. At higher speeds, the effect becomes dramatic. Travel at 90% of light speed, and time for you passes at about half the rate of a stationary observer. At 99.9% of light speed, the factor is about 22. For every year you experience, 22 years pass on Earth. Approach light speed closely enough, and you could cross the galaxy in what feels like years, while millennia pass outside. This isn't science fiction. It's the demonstrated structure of space-time. Time is not absolute. It flows at different rates depending on motion and gravity. Your now and someone else's now can be different moments, separated by seconds or years, and both perspectives are equally valid. It means time is personal, local, woven into your relationship with the rest of the universe. There's no master clock ticking away somewhere, just countless individual timelines, each valid within its own frame of reference, sometimes synchronized, sometimes wildly divergent. Cool certain materials below a critical temperature, and they become superconductors, materials with zero electrical resistance. Current flows through them without any energy loss, persisting indefinitely. But superconductors have another remarkable property. They expel magnetic fields completely from their interior. This is called the Meissner effect. When a material becomes superconducting, any magnetic field that was passing through it gets pushed out. The superconductor generates surface currents that create an opposing magnetic field, perfectly canceling the external field inside. If you place a magnet above a superconductor, the expulsion of the magnetic field creates a repulsive force that lifts the magnet, suspending it in midair. The result is stable levitation. The magnet hovers, and if you push it down, it pushes back. If you lift it, it settles back to its equilibrium height. You can even flip the superconductor over, and the magnet will hang beneath it, defying gravity. It's called quantum locking, and it looks like magic. A small magnet floating motionless above a disk, held by invisible forces. This happens because of quantum mechanical effects. Superconductivity arises when electrons pair up and move coherently through the material without scattering. This quantum coherence produces the perfect diamagnetism of the Meissner effect. Scientists are exploring practical applications. Magnetic levitation trains that glide frictionlessly on superconducting tracks, lossless power transmission, ultra-sensitive magnetic sensors. The challenge is that most superconductors only work at extremely cold temperatures, requiring expensive cooling. But high-temperature superconductors, discovered in recent decades, work at less extreme conditions, making practical applications more feasible. For now, superconducting levitation remains mostly a laboratory demonstration, a visible manifestation of quantum mechanics at work. But it hints at a future where friction becomes optional, where materials can manipulate magnetic fields with perfect precision, where quantum effects shape everyday technology. Water's surface behaves like a stretched membrane, an invisible skin that can support weight. This surface tension allows water striders to walk on ponds, needles to float if placed carefully, and droplets to hold spherical shapes against gravity. Surface tension arises from cohesion, water molecules attracting each other. Inside the bulk liquid, each molecule is pulled equally in all directions by its neighbors. But at the surface, molecules are pulled only sideways and downward, creating an imbalance. The surface molecules pull together more tightly, forming a kind of elastic sheet. This isn't strong enough to support large objects. You can't walk on water, but at small scales, it's surprisingly powerful. Insects take advantage of it. Water striders have legs covered with tiny hairs that distribute their weight and resist getting wet. When they stand on water, they create dimples in the surface without breaking through, like pressing on a trampoline. The surface tension pushes back, supporting them. Even objects denser than water can float if they're small enough and properly shaped. A steel needle will sink if dropped vertically, but if placed horizontally with care, surface tension can support it. The needle creates a depression in the surface, and the tension provides an upward force that counteracts gravity. Surface tension also explains why water forms droplets. In the absence of other forces, surface tension pulls water into the shape that minimizes surface area, a sphere. That's why raindrops are round, when they're small enough that air resistance doesn't flatten them. Why bubbles are spherical, why mercury beads up on surfaces. It's a reminder that at small scales, forces we barely notice become dominant. Surface tension is negligible when you're swimming, but for a beetle walking on a pond, it's the difference between solid ground and drowning. Light travels at 186,000 miles per second in vacuum, the cosmic speed limit, unchangeable and absolute. Except it's not quite unchangeable. Light slows down when passing through transparent materials. It moves slower in water than air, slower in glass than water, but the slowdown is modest. Light in glass still travels at about 2/3 its vacuum speed. But in 1999, physicist Lene Howe and her team achieved something extraordinary. They slowed light to 38 miles per hour, bicycle speed, by passing it through an exotic state of matter called a Bose-Einstein condensate. They created this condensate by cooling sodium atoms to within a few billionths of a degree above absolute zero. At such extreme cold, the atoms enter a quantum state where they all share the same wave function, behaving as one coherent entity. When light enters this condensate, it interacts with the atoms in a way that drastically reduces its speed. Later experiments went further, stopping light completely, capturing it in the condensate, holding it stationary, then releasing it to continue its journey. Light, which never stops in ordinary circumstances, was frozen in place. What's happening isn't that individual photons are slowing down. Photons always move at light speed. Rather, photons are being absorbed and re-emitted by atoms in a coordinated way that makes the pulse of light as a whole propagate slowly. These experiments aren't just curiosities. They have potential applications in quantum computing and information storage. Imagine capturing light pulses carrying data, holding them in quantum memory, then releasing them when needed. The ability to control light's speed opens new possibilities for manipulating information. But beyond practical applications, there's wonder in the fact itself. Light, which defines the ultimate speed, can be coaxed into crawling, slowed to speeds where you could outrun it on a bike. The double-slit experiment is physics made mystical. It's simple enough to describe, yet strange enough to unsettle anyone who thinks carefully about what it means. Send individual electrons through two slits in a barrier. If you don't observe which slit each electron passes through, they create an interference pattern on the detector behind, alternating bands of high and low probability, exactly like waves would. Each electron seems to pass through both slits simultaneously, interfering with itself. But if you measure which slit the electron passes through, if you observe it, the interference pattern disappears. The electrons start behaving like particles, going through one slit or the other, creating two simple bands aligned with the slits. The act of observation changes the outcome. Not because the measurement disturbs the electron mechanically, but because measurement collapses the quantum superposition. Before observation, the electron exists in a state that includes both paths. Observation forces it to choose. This isn't a limitation of our measurement technology. It's how reality works at the quantum level. Particles don't have definite trajectories until measured. They exist as probability waves, spread across multiple possibilities, collapsing into specific outcomes only when interaction occurs. Physicists have performed variations of this experiment countless times, with different particles, different configurations, and the result is always the same. The universe behaves differently depending on whether or not you look. It's as if reality is context-dependent, as if the universe remains undecided about certain properties until forced to commit. What does it mean? Interpretations vary. Some say observation creates reality. Others say reality branches into multiple outcomes. Still, others embrace mathematical formalism without claiming to know what it means. But everyone agrees on the experimental facts. Observation matters, particles behave like waves, quantum mechanics is profoundly strange. Friction is invisible most of the time, unnoticed as we walk or slide or turn, but it's consuming enormous amounts of energy, roughly 20% of all the energy humanity uses. That's energy converted to heat through friction in engines, transmissions, bearings, tires, machinery of every kind. We usually think of friction as useful. It lets us walk without slipping, lets brakes stop cars, lets nails hold boards together. And it is useful, essential even, but it's also wasteful. Every time surfaces rub against each other, some of the energy that could be doing useful work gets converted to heat instead. In an engine, friction between pistons and cylinders, between gears and bearings, dissipates energy that could otherwise propel the vehicle. In industrial machinery, friction in joints and contacts requires constant energy input just to overcome resistance. Globally, it adds up to staggering losses. Engineers fight friction constantly, with lubricants, with precision manufacturing, with new materials that slide more easily. Every reduction in friction means more efficiency, less energy wasted as heat. It's why oil is so important to machinery, why ball bearings revolutionized mechanical engineering, why scientists develop exotic low-friction coatings. And yet, despite centuries of studying friction, we still don't fully understand it at the atomic level. We know it involves irregularities in surfaces catching on each other, adhesive forces between materials, energy dissipation through deformation. But the precise mechanisms, especially at nanoscale, remain surprisingly complex and not completely resolved. Friction is everywhere, omnipresent and ancient, older than life itself. Rocks scraping across each other, ice sliding down mountains, wind eroding stone. Friction shapes the landscape and consumes the energy of every moving thing. It's a fundamental feature of our physical world, simultaneously essential and wasteful. Simple in concept, yet complex in detail. You've heard the Doppler effect countless times. The way an ambulance siren rises in pitch as it approaches, then drops as it passes and moves away. It's so familiar it seems unremarkable, but it's revealing something profound about waves and motion. When a sound source moves toward you, each wave crest is emitted from a position slightly closer than the previous one. The waves get compressed, their wavelengths shortened, which means higher frequency, higher pitch. When the source moves away, the opposite happens. Waves stretch out, wavelengths lengthen, frequency drops, pitch lowers. The effect works with any wave. Light experiences it too. Objects moving toward us have their light shifted toward shorter wavelengths, bluer. Objects moving away are shifted toward longer wavelengths, redder. Astronomers use this to measure the motion of stars and galaxies. And here's where it becomes cosmologically important. Almost every distant galaxy shows a redshift. Their light is stretched to longer wavelengths, meaning they're moving away from us. And the farther away they are, the faster they're receding. This was one of the key observations that led to our understanding of the expanding universe. Edwin Hubble, in the 1920s, measured these redshifts and found the pattern. Distance correlates with recession velocity. Galaxies aren't just moving randomly. They're all moving away from each other as space itself expands. The Doppler effect observed in the light from distant galaxies revealed the universe's expansion. It's remarkable that the same effect that makes sirens change pitch also tells us the universe is expanding, that space is stretching, carrying galaxies apart. A simple consequence of wave physics, observable with sound on Earth, extends to light across the cosmos and reveals the fundamental dynamics of reality itself. Imagine a liquid that responds to magnets, forming spikes and valleys and intricate patterns as if it were alive. Ferrofluids are this strange hybrid, liquids embedded with tiny magnetic nanoparticles, usually iron oxide, suspended in oil or water with surfactants to prevent clumping. In the absence of a magnetic field, ferrofluids look like ordinary black liquids. But bring a magnet near, and they transform. Spikes erupt from the surface, pointing toward the magnet like tiny mountains. Move the magnet, and the spikes follow, flowing and reshaping. The patterns are mesmerizing, geometric, organic, constantly shifting. These spikes form because of competing forces. The magnetic field wants to pull the fluid toward the magnet. Surface tension wants to keep the surface smooth. Gravity pulls downward. The equilibrium between these creates the characteristic spike pattern, minimizing surface area while allowing the magnetic particles to align with the field. Ferrofluids aren't just aesthetic curiosities. They have practical applications. They're used in loudspeakers, where they cool voice coils and dampen vibrations. They seal rotating shafts in hard drives and other devices. They're used in experimental cancer treatments, where magnetic particles are injected into tumors and heated with alternating magnetic fields. But beyond utility, there's something hypnotic about watching ferrofluids respond to magnets. The liquid seems to have intention, reaching toward the magnetic source, flowing around it, creating structures that dissolve and reform. It's matter caught between two states, fluid and magnetic, creating behavior that's neither quite liquid nor quite solid, but something in between, something that seems almost biological in its responsiveness. Perhaps it reminds us that the line between animate and inanimate is blurrier than we think. Give matter the right properties, and it can appear purposeful, responsive, alive. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice, one atom thick. You could stack 3 million sheets of graphene, and the stack would be only 1 millimeter tall. And yet this impossibly thin material is about 200 times stronger than steel by weight. It's the thinnest material possible. You can't make anything thinner than one atom. But that atomic thinness doesn't mean fragility. The carbon-carbon bonds in graphene are incredibly strong, and the hexagonal arrangement distributes stress efficiently. The result is extraordinary tensile strength. A sheet of graphene strong enough to support an elephant would weigh less than one of the elephant's whiskers. It's a staggering strength-to-weight ratio, unmatched by any conventional material. Graphene also conducts electricity and heat exceptionally well. It's nearly transparent. It's flexible, able to bend and stretch without breaking. These properties make it fantastically promising for applications. Flexible electronics, ultra-strong composites, efficient solar cells, advanced batteries, water filtration, medical devices. The challenge is production. Making large, high-quality sheets of graphene cheaply remains difficult. Scientists can create small samples in laboratories, but scaling up to industrial production has proven challenging. Still, progress continues, and graphene-based products are beginning to appear commercially. What's remarkable is that graphene is just carbon, the same element in coal, diamonds, your body. Arrange it differently, and you get wildly different properties. Graphite is soft, crumbly, used in pencils. Diamond is hard, crystalline. Graphene is strong, flexible, conductive. Same atoms, different structures, different worlds of possibility. It reminds us that configuration matters as much as composition. The universe is built from a limited set of elements, but the arrangements are infinite, creating diversity and complexity from simple building blocks. For centuries, inventors have tried to create perpetual motion machines, devices that run forever without external energy input, sometimes even producing extra energy. Countless designs have been proposed, built, patented, and every single one has failed because they violate the fundamental laws of thermodynamics. The first law states that energy is conserved. You can't create or destroy it, only convert it from one form to another. So a machine that produces more energy than it consumes is creating energy from nothing, which is impossible. The second law states that entropy disorder always increases in closed systems. Energy transformations are never perfectly efficient. Some energy always dissipates as heat, becoming unavailable for useful work. So even if you don't want extra energy, just a machine that runs forever at constant output, friction and heat loss will eventually slow it down. Bearings wear, lubricants degrade, heat radiates away. Everything tends toward equilibrium, toward stillness. Some proposed perpetual motion machines are clever, hiding their energy sources or losses in subtle ways. Machines that seem to run on magnets alone, or gravity, or capillary action. But careful analysis always reveals the hidden flaw, a subtle energy input, an overlooked source of friction, a misunderstanding of how forces work. The impossibility isn't technological. It's not that we haven't found the right materials or design. It's that the universe doesn't permit it. The laws of thermodynamics are among the most fundamental and inviolable principles in physics. And perhaps that's okay. The universe runs on energy gradients, on differences in temperature and pressure and chemical potential. Everything flows from high energy to low, from order to disorder, eventually reaching equilibrium. Perpetual motion would mean escaping this flow, and the universe doesn't offer that escape. 2 trillion galaxies. The number is almost meaningless, too large to visualize, too vast to comprehend. But that's our current estimate for how many galaxies exist within the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. Each of these galaxies contains anywhere from millions to hundreds of billions of stars. Our own Milky Way has perhaps 200 to 400 billion stars. Multiply that by 2 trillion galaxies, and you get a number of stars so large it defies imagination. Somewhere around 1024, a trillion stars. And we can only see a fraction of what exists. The observable universe is limited by the speed of light and the age of the universe. Light from more distant regions simply hasn't had time to reach us yet. Beyond our cosmic horizon, there could be infinitely more galaxies, forever invisible to us because their light will never arrive. Early estimates of galaxy counts were much lower. The Hubble Space Telescope's deep field images, photographs of seemingly empty patches of sky, revealed thousands of galaxies where none were visible before. Each refinement of our instruments reveals more, dimmer, more distant galaxies that previous surveys missed. 2 trillion galaxies, each a vast island of stars, most containing billions of solar systems, many likely harboring planets. The scale suggests that even if life is extraordinarily rare, the sheer number of opportunities means we're probably not alone. Somewhere in those 2 trillion galaxies, perhaps in millions or billions of locations, other beings might exist, looking up at their own night sky, contemplating the same vastness. It's humbling and oddly comforting. We're infinitesimally small in this cosmos, our galaxy one among trillions, our star one among billions within that galaxy, our planet one among countless worlds. And yet we're here, conscious, capable of measuring and marveling at the immensity. The universe made observers, at least once. Perhaps it's done so many times over. Every second, the sun converts 4 million tons of matter into pure energy through nuclear fusion. 4 million tons simply ceases to exist as matter, transforming instead into the light and heat that make life on Earth possible. This is E to mc2 made real. Einstein's famous equation tells us that mass and energy are interchangeable. Matter is just extremely concentrated energy. The conversion rate is determined by C2, the speed of light squared, which is an enormous number. So even a small amount of mass converts into tremendous energy. In the sun's core, hydrogen nuclei, protons, overcome electromagnetic repulsion through quantum tunneling and fuse together, forming helium. The helium nucleus weighs slightly less than the 4 protons that created it. That missing mass, about 0.7% of the original, becomes energy, released as photons. 4 million tons per second sounds catastrophic, like the sun is rapidly consuming itself. But the sun is so massive, about 2 × 10^30 kilograms, that losing 4 million tons per second is negligible. It's been burning at roughly this rate for 4.6 billion years, and has enough fuel to continue for another 5 billion. The energy produced takes a strange journey. Photons created in the core bounce around inside the sun, absorbed and re-emitted by atoms millions of times. It can take tens of thousands to hundreds of thousands of years for that energy to random walk from core to surface. Only then does it escape as sunlight, traveling 8 minutes to Earth. So the sunlight falling on your face right now began as matter in the sun's core, perhaps 100,000 years ago. Converted to energy through fusion, slowly worked its way outward, and finally streamed across space to warm your skin. You're feeling ancient energy, matter turned light, the universe's most fundamental transformation made tangible. When you look at the most distant galaxies visible to our telescopes, you're seeing them as they were over 13 billion years ago, when the universe was young, just a few 100 million years old, still forming its first stars and galaxies. The light from these galaxies has been traveling through space for almost the entire history of the universe. It left those galaxies when they were newly formed, just coalescing from primordial hydrogen and helium, and has been journeying through expanding space ever since. Those galaxies don't look like that anymore. By now, 13 billion years later, they've evolved, merged with other galaxies, perhaps disappeared entirely. We're seeing their infancy, their birth, frozen in the light that's been traveling toward us across cosmic time, and we can never see them as they are now. By the time light showing their current state reaches us, another 13 billion years will have passed. We're locked into viewing the past. The farther we look, the deeper into history we see. This creates a strange situation. The universe has no now in a global sense. When we look around, we see different times. Nearby stars appear as they were years ago. Distant galaxies appear as they were billions of years ago. Our view of the cosmos is a mosaic of different eras, a timeline spread across space. The most distant objects we can detect are from the era of recombination, when the universe first became transparent to light, about 380,000 years after the Big Bang. We see this as the cosmic microwave background, ancient light that's been traveling for 13.8 billion years, stretched by expansion into microwave wavelengths. Beyond that is a wall we can't see past. Not because space ends, but because before recombination, the universe was opaque. Our vision reaches a limit not in space, but in time. The Milky Way isn't stationary. Along with hundreds of thousands of other galaxies in our region of space, we're being pulled towards something massive, an enormous gravitational anomaly called the Great Attractor. It's located about 150 to 250 million light years away, in the direction of the constellations Hydra and Centaurus. We're moving toward it at about 600 kilometers per second, dragged by its immense gravitational pull. But here's the problem. The Great Attractor lies behind the zone of avoidance, a region obscured by the dense plane of our own Milky Way galaxy. Dust and stars block our view, making it difficult to see what's actually there. From what we can observe, the Great Attractor appears to be a large concentration of mass, possibly a massive cluster or supercluster of galaxies. But even this enormous structure might not fully explain the motion. Recent observations suggest there's something even larger beyond it. The Shapley supercluster, an even more massive collection of galaxies pulling on everything in this region of space. It's humbling to realize that our entire galaxy, along with hundreds of thousands of neighbors, is being pulled through space by gravitational forces from structures so massive and distant we can barely map them. We're not just orbiting within the Milky Way. We're part of larger scale motions, currents in the cosmic ocean, flowing toward concentrations of mass we're still working to understand. The universe has structure at every scale. Stars in galaxies, galaxies in clusters, clusters in superclusters, all connected by gravity, all moving in response to the distribution of matter. We're passengers on this journey, pulled by forces originating from masses far beyond our immediate cosmic neighborhood. Right now, as you rest here, billions upon billions of neutrinos are streaming through you. From the sun alone, about 100 billion neutrinos pass through every square centimeter of your body every single second. They enter from above, pass through flesh and bone without slowing, and exit below, continuing their journey through the earth as if it weren't there. Neutrinos are ghostly particles, nearly massless, electrically neutral, interacting so weakly with matter that they pass through almost everything. The entire Earth is essentially transparent to them. Most neutrinos travel through our planet without touching a single atom. They're created in the sun's core as a byproduct of fusion reactions. While photons take tens of thousands of years to random walk from the sun's core to its surface, neutrinos just stream out directly. They carry information about what's happening in the solar core right now, not hundreds of thousands of years ago. Detecting neutrinos requires enormous, sophisticated detectors, vast tanks of water or other materials buried deep underground to shield them from cosmic rays. Even then, only a tiny fraction of passing neutrinos interact. A detector might capture a few neutrinos per day from the trillions passing through it. Despite being so common, the universe is filled with neutrinos from stars, supernovae, the Big Bang itself. They remain mysterious. We know they have mass, but we don't know exactly how much. We know they come in 3 types and can oscillate between them. But many properties remain uncertain. You're constantly bathed in these particles, immersed in an invisible stream flowing from the sun, from distant stars, from the cosmic background. The universe is more permeable than it appears. Matter isn't as solid as it seems. We're porous to certain forms of reality, transparent to forces we can barely detect. The universe is glowing. Not visibly, the light has been stretched by expansion into microwave wavelengths, but it's there, filling all of space with a faint, nearly uniform radiation. This is the cosmic microwave background, the oldest light in existence, the afterglow of creation itself. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, a dense fog of plasma where photons couldn't travel freely. But when atoms formed, the fog cleared. Photons that had been trapped suddenly streamed freely through space. Those photons are still traveling, stretched by 13.8 billion years of cosmic expansion. They've cooled from visible light to microwaves, maintaining a nearly perfect blackbody spectrum at about 2.7 Kelvin, just 2.7 degrees above absolute zero. This radiation comes from every direction, filling the entire sky. It's not from a specific source or location. It's from the moment when the whole observable universe became transparent. Every point in space was part of that release, so the radiation surrounds us uniformly. Tiny variations in the temperature, fluctuations of about 1 part in 100,000, reveal the seeds of structure in the early universe. Regions that were slightly denser eventually collapsed under gravity to form galaxies and clusters. The cosmic microwave background is a baby picture of the universe, showing the initial conditions that led to everything we see today. When you tune a television to static between channels, about 1% of that noise is the cosmic microwave background. You're seeing or hearing the echo of the Big Bang, ancient light transformed into snow on a screen, the universe whispering its origin story. When we say planets orbit the sun, we're simplifying. More accurately, every planet and the sun both orbit their common center of mass, the barycenter. For small planets, this barycenter lies deep inside the sun, so it looks like the planet orbits while the sun stays still. But Jupiter is massive, about 318 times Earth's mass, containing more mass than all other planets combined. Its gravity is strong enough that the barycenter between Jupiter and the sun lies outside the sun's surface, about 46,000 kilometers above it. This means Jupiter and the sun both orbit this point in empty space. The sun wobbles as Jupiter pulls it around their shared center of mass. If you watched from far away, you'd see both objects circling a point just beyond the sun's edge. This wobble is how we detect exoplanets around distant stars. We can't see the planets directly, they're too small and dim. But we can see the star wobble as it orbits the barycenter it shares with its planets. By measuring this wobble through Doppler shifts in the star's light, we infer the presence of planets and estimate their masses and orbits. The sun's wobble from Jupiter is large enough that if aliens in a nearby star system were watching our sun with the same techniques we use, they detect Jupiter easily. They might detect Saturn too. Earth would be much harder. Our mass is too small to create much wobble. It's a reminder that orbital mechanics is reciprocal. Nothing orbits something else without affecting it. Every gravitational relationship involves mutual motion, both objects responding to each other, dancing around their shared center of mass. Voyager 1 has been traveling for over 47 years now, moving farther from Earth than any human-made object in history. It's currently more than 15 billion miles away, so distant that radio signals, traveling at light speed, take over 22 hours to reach it. Launched in 1977, Voyager 1 visited Jupiter and Saturn, sending back stunning images and data before continuing outward. In 2012, it crossed the heliopause, the boundary where the solar wind gives way to interstellar space. It's now the only human-made object traveling through the space between stars. Its power supply, generated by decaying plutonium, is slowly fading. Engineers have been shutting down non-essential systems to conserve energy. Eventually, probably in the mid-2020s, it will no longer have enough power to operate its instruments. It will go silent, continuing its journey through the void without speaking to us. But even then, it will carry the golden record, a phonograph record containing sounds and images from Earth, greetings in multiple languages, music from different cultures. It's a message in a bottle cast into the cosmic ocean, intended for any intelligent beings who might one day encounter it. The odds of that happening are infinitesimally small. Space is vast and mostly empty. Voyager will likely drift for billions of years without passing close to any star or planet. But it's there, carrying a piece of Earth into eternity, a testament to human curiosity and the desire to reach beyond our boundaries. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. It will be our silent ambassador, traveling forever through the dark. It's a comparison that's become famous, perhaps overused, but it remains staggering. The number of stars in the observable universe exceeds the number of grains of sand on all of Earth's beaches. Estimates for grains of sand vary, but a common figure is around 7.5 x 10^18, 7 quintillion grains. That's counting every beach, every desert, every grain of sand on Earth's surface. The number of stars is much larger, with about 2 trillion galaxies, each containing billions to hundreds of billions of stars. We get roughly 10 to 24 stars, a trillion, or a septillion. So there are more than 100,000 stars for every grain of sand on Earth. Let that settle. Every grain you've ever touched, every beach you've walked on, every desert in the world. Multiply all that sand by 100,000, and you're approaching the number of stars. And yet, paradoxically, there are more atoms in a single grain of sand than there are stars in the observable universe. A grain of sand contains roughly 1020 atoms, far more than the 1024 stars that exist. The very small outnumbers the very large. These comparisons help us grasp scale, though they're ultimately inadequate. Numbers this large transcend intuition. We can write them, calculate with them, but we can't truly visualize them. The universe's scale, both large and small, exceeds the grasp of human imagination. But perhaps that's part of the wonder. We're creatures of middle scales, evolved to navigate meters and kilograms, seconds and minutes. The cosmic and the quantum lie beyond our intuitive reach, yet we found ways to measure and understand them anyway. The moon is leaving us, slowly, imperceptibly, but inexorably, drifting away at about 3.8 centimeters per year. That's roughly the rate your fingernails grow, translated into cosmic separation. This happens because of tidal interactions. The moon's gravity creates tidal bulges in Earth's oceans. But Earth rotates faster than the moon orbits, so these bulges are dragged ahead of the moon. The bulge's gravity pulls the moon forward in its orbit, speeding it up slightly. and when an orbiting object speeds up, it moves to a higher orbit, farther away. Meanwhile, the moon's gravity pulling on those tidal bulges slows Earth's rotation. Days are getting longer, about 1.7 milliseconds per century. In Earth's deep past, days were much shorter, perhaps only a few hours long when the moon first formed. The moon was also much closer, appearing enormous in the sky. Billions of years from now, assuming both Earth and Moon survived the Sun's eventual expansion into a red giant, the Moon will be much farther away. Total solar eclipses, where the Moon perfectly covers the Sun's disk, will no longer be possible. The Moon will appear too small. Right now, we live in a brief cosmic moment where the Moon's apparent size almost exactly matches the Sun's, allowing for perfect total eclipses. This is pure coincidence. The Moon is 400 times smaller than the Sun, but also 400 times closer. In the past, the Moon was too large, blocking too much sky. In the future, it will be too small. We happen to exist in the narrow window where they match. The Moon is drifting, days are lengthening, and the cosmic clockwork continues its slow, inevitable evolution. Saturn's magnificent rings, the feature that makes it instantly recognizable, the crown jewel of our solar system, are temporary. They're disappearing, raining down onto the planet in a steady stream of icy particles, and in roughly 100 million years, they'll be gone. The rings are mostly water ice, ranging from dust-sized grains to house-sized chunks. Saturn's magnetic field interacts with these particles, charging them and pulling them inward. Additionally, micrometeoroids constantly bombard the rings, vaporizing ice that then falls towards Saturn. Combined, these processes remove ring material at a rate equivalent to an Olympic swimming pool's worth every 30 minutes. 100 million years sounds like a long time, and it is by human standards. But it's a blink in cosmic terms. Saturn has existed for over 4 billion years. If the rings have been around the whole time, why are they disappearing now? The answer suggests the rings might be young, perhaps only 100 to 200 million years old. They might have formed from the breakup of a moon that wandered too close to Saturn and was torn apart by tidal forces. Or perhaps a collision between moons created the debris. Either way, we might be living in the relatively brief period when Saturn has rings. Imagine the ancient Earth 100 million years ago, dinosaurs roaming beneath skies that would never see a ringed Saturn. It looked bare. And imagine Earth 100 million years hence, when Saturn will have lost its defining feature, appearing as just another gas giant. We're fortunate to exist in this window. Saturn's rings are a temporary sculpture, cosmic artwork that won't last. Future generations, if they exist billions of years from now, might look at images from our era and marvel that we witnessed Saturn adorned with rings, something they'll only know from ancient photographs and distant memory. Venus is strange in many ways, but perhaps the strangest is its rotation. A single day on Venus, one complete rotation on its axis, takes 243 Earth days. Meanwhile, Venus completes one orbit around the Sun in only 225 Earth days. This means Venus's year is shorter than its day. The planet completes an orbit before it finishes a single rotation. And to make things even more peculiar, Venus rotates backward, retrograde, compared to most planets. If you could stand on Venus's surface and survive the crushing pressure and searing heat, you'd see the sun rise in the west and set in the east, and it would take 116 Earth days from sunrise to sunset. Why does Venus rotate so slowly and backward? We're not entirely sure. The most likely explanation involves ancient collisions. Early in the solar system's history, Venus might have been struck by large planetesimals that altered its rotation, or tidal forces from the Sun, combined with atmospheric effects, might have gradually slowed and reversed its spin over billions of years. The result is a world profoundly out of sync with the rhythm most planets follow. Where Earth spins comfortably through day and night every 24 hours, Venus languishes, turning so slowly that months pass between sunrise and sunset. It's a reminder that planetary characteristics we take for granted, like day length, aren't universal. Earth's 24-hour day feels fundamental to us, but it's just one possibility among many. The universe contains worlds where years pass in days, where suns rise in the wrong direction, where the familiar rhythms of light and dark become unrecognizable. Venus stands as a warning, perhaps, of how different worlds can be, even neighboring ones in the same solar system. Our galaxy, the Milky Way, is on a collision course with Andromeda, the nearest large galaxy. They're approaching each other at about 110 kilometers per second, and in roughly 4 to 5 billion years, they'll collide. Collide might be the wrong word. Galaxies are mostly empty space. Stars are separated by such vast distances that when two galaxies merge, actual stellar collisions are extraordinarily rare. Instead, the galaxies will pass through each other, their gravitational fields interacting, pulling and distorting each other's shapes. The process will take millions of years. The galaxies will approach, interpenetrate, draw apart, then fall back together again, eventually merging into a single elliptical galaxy, sometimes called Milkomeda in informal discussions. Star formation will spike as gas clouds collide. New structures will emerge from the chaos. Should we worry? Not immediately. The Sun will likely survive the merger, though its position within the new galaxy might change dramatically. By the time this happens, the Sun will already be swelling into a red giant, making Earth uninhabitable anyway. The galactic merger is the least of future Earth's problems, but imagine witnessing it. Andromeda, currently a faint smudge visible to the naked eye, will grow larger in the sky over millions of years, eventually dominating the night sky as a brilliant band of stars. The two galactic cores will dance around each other, spiraling inward until they merge into a single supermassive black hole. It's happening all across the universe. Galaxies merge regularly, growing through countless collisions over cosmic time. Our own Milky Way has absorbed dozens of smaller galaxies already. Andromeda will just be the largest merger in our future, two massive galaxies becoming one. Neutron stars are the collapsed cores of massive stars, city-sized spheres containing more mass than the Sun. And some of them spin at absolutely staggering rates, hundreds of rotations per second. These rapidly rotating neutron stars are called pulsars when their magnetic fields and rotation axes are misaligned, creating beams of radiation that sweep across space like a lighthouse. We detect these as regular pulses, hence pulsar, some arriving hundreds of times per second. The fastest known pulsar, PSR J1748-2446 AD, rotates 7 to 16 times per second. Its surface is moving at roughly 24% of the speed of light. Material at the equator experiences such extreme centrifugal forces that it's barely held down by gravity. A slightly faster spin would tear the star apart. How do they spin so fast? Conservation of angular momentum. When a massive star's core collapses during a supernova, it shrinks from thousands of kilometers across to about 20 kilometers. Like a figure skater pulling in their arms, this contraction dramatically increases rotation speed. A star that rotated once per month might become a neutron star, rotating hundreds of times per second. Over time, pulsars slow down as they emit radiation, gradually losing rotational energy. But some pulsars, called millisecond pulsars, are spun back up by stealing matter from a companion star. The infalling material carries angular momentum, adding spin to the neutron star, accelerating it to extreme rotation rates. The physics at these speeds is almost incomprehensible. Surface gravity billions of times stronger than Earth's, magnetic fields trillions of times stronger than any we can create, matter compressed to nuclear densities, all spinning hundreds of times per second. Neutron stars are laboratories for extreme physics. This sounds like fiction, but it's based on real chemistry. Astronomers have detected a substance called ethyl formate in the gas cloud at the center of our galaxy. Ethyl formate is the chemical compound that gives raspberries their flavor and contributes to rum's distinctive smell. Obviously, no one has actually smelled or tasted the galactic center. It's 26,000 light years away. And even if you could reach it, the conditions near a supermassive black hole surrounded by intense radiation would be instantly lethal. But radio telescopes can detect the unique spectral signatures of molecules in space. Different molecules absorb and emit light at specific frequencies, creating fingerprints astronomers can identify. By analyzing these signatures in the radio waves coming from the galactic center, scientists identified ethyl formate among many other organic molecules. Space is full of organic chemistry. Vast molecular clouds contain alcohols, sugars, amino acids, the building blocks of life and flavors. There's a cloud called Sagittarius B2 that contains billions of liters of alcohol, mostly methanol and ethanol, along with various flavor compounds. Does this mean anything profound? Perhaps. The universe naturally produces complex organic molecules. The chemistry that creates flavors on Earth also occurs in space, suggesting that the chemical pathways leading toward life might be common, even inevitable. Or perhaps it's just a delightful coincidence, a reminder that chemistry is chemistry wherever it occurs. The same molecules that make raspberries delicious exist in clouds of gas orbiting the center of our galaxy, connecting the mundane and the cosmic through shared molecular structure. Either way, it's wonderfully strange to know that our galactic center, in some abstract chemical sense, smells like fruit and rum. Olympus Mons is a mountain almost beyond belief. Rising about 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest, it's the tallest known mountain in the solar system, and it's enormous not just in height, but in breadth. Its base spans roughly 600 kilometers, large enough to cover the entire state of Arizona. It's a shield volcano, similar in shape to Hawaiian volcanoes, but vastly larger. The slopes are relatively gentle. You could walk up much of it without realizing you were climbing a mountain. From the summit, the curvature of Mars would prevent you from seeing the base. The horizon would cut off your view, making it seem like you're standing on an endless plain tilted slightly upward. Why is Olympus Mons so large? Mars lacks plate tectonics. On Earth, tectonic plates move, carrying volcanoes away from their magma sources. Hawaiian volcanoes form a chain as the Pacific Plate moves over a stationary hotspot. Each volcano grows for a while, then drifts away, and a new one begins. But Mars has no moving plates. A volcano can sit over its magma source for billions of years, continuously erupting and building upward. Olympus Mons formed this way, growing layer upon layer, becoming a structure so massive it strains the limits of what rocky planets can support. Mars's lower gravity also helps. On Earth, a mountain that tall would collapse under its own weight. But Mars's gravity is only 38% of Earth's, allowing structures to grow taller without crumbling. Olympus Mons is likely extinct now. Mars's volcanic activity has largely ceased, but the mountain remains, a monument to billions of years of eruptions, a geological feature Earth could never sustain. The moon feels close. On a clear night, it dominates the sky, its features visible to the naked eye. But it's actually farther away than most people imagine, about 384,000 kilometers on average. That distance is large enough to fit every planet in the solar system between Earth and the moon, lined up side by side. Jupiter, Saturn, Uranus, Neptune, plus the rocky planets, all of them in a row, would span about 380,000 kilometers. There would even be a little space left over. This surprises people because we tend to think of the moon as nearby, practically touching Earth in astronomical terms. And compared to other cosmic distances, it is close. But close is relative. The moon is about 30 Earth diameters away. That's not trivial distance. If Earth were the size of a basketball, the moon would be a tennis ball about 7 meters away. The scale is larger than our mental models suggest. This gap has practical implications. Radio signals traveling at light speed take about 1.3 seconds to reach the moon and return. Apollo astronauts experienced this delay in communications, a noticeable pause between speaking and receiving a response from Houston. The distance also varies. The moon's orbit is elliptical, so sometimes it's closer, perigee about 363,000 kilometers, and sometimes farther, apogee about 405,000 kilometers. At apogee, you couldn't quite fit all the planets. Saturn would stick out a bit. But at average distance, they all fit. A reminder that even in our local neighborhood, space is spacious. Distances are larger than they seem, and our intuitions about scale often need correction. In September 2015, humanity detected something extraordinary for the first time: gravitational waves. These are ripples in the fabric of space-time itself, caused by violent cosmic events like colliding black holes or neutron stars. Einstein predicted them a century earlier. General relativity describes gravity not as a force, but as the curvature of space-time. Massive objects create wells in this fabric, and when massive objects accelerate, especially when they orbit each other at relativistic speeds, they create ripples that propagate outward at the speed of light. These waves are unimaginably subtle. The first detected gravitational wave, from two black holes merging 1.3 billion light-years away, caused space itself to stretch and compress by about 1/10,000th the width of a proton. Detecting this required instruments of extraordinary precision. Laser interferometers with arms several kilometers long capable of measuring distance, changes smaller than the nucleus of an atom. But they detected it, and since then, dozens more have been observed. Each detection opens a new window on the universe. We're no longer limited to electromagnetic radiation, light in all its forms. We can now observe gravitational radiation, events that produce no light but shake the very structure of space. Colliding black holes produce no light. They're dark objects merging in darkness, but they ring space-time like a bell, sending gravitational waves across the cosmos. We can now hear these events, translating the waves into sound, listening to the universe's most violent phenomena. It's a new sense. For all of human history, we've observed the universe through light. Now we can feel the trembling of space-time, detecting events invisible to any telescope, expanding our awareness of the cosmos in profound new ways. The universe is expanding, and in its most distant regions, space is stretching faster than light can travel. This sounds like it violates relativity. Nothing can move faster than light, right? But relativity's speed limit applies to objects moving through space. It doesn't constrain space itself from expanding. And in the most distant regions of the observable universe, space is expanding so rapidly that galaxies are receding from us faster than light. This means we can never see those galaxies as they are now. Light they emit today will never reach us because the space between us is expanding faster than the light can cross it. These galaxies are beyond our cosmic horizon, permanently disconnected from our observable universe by expansion. There's even a term for the boundary, the cosmic event horizon. Beyond it lie galaxies we can currently see, because the light left them billions of years ago when they were closer, but that we'll never see in their present state. Over time, as expansion continues, more and more galaxies will cross this horizon, disappearing from our view. Far in the future, if expansion continues accelerating, distant observers will see an increasingly empty universe. Galaxies beyond their local group will have receded beyond their horizon, vanished. They'll look out and see only darkness, perhaps concluding they're alone in a vast, empty cosmos. We're fortunate to live when we do. The universe is still young enough. Expansion hasn't yet isolated us completely. We can see a rich cosmos, billions of galaxies, the cosmic microwave background. Future civilizations might not have that privilege. The coldest known place in the universe isn't in the depths of space, in the shadow of some distant moon, or in the void between galaxies. It's here on Earth, in our laboratories, where scientists have achieved temperatures billionths of a degree above absolute zero. Space is cold, yes. The cosmic microwave background radiation gives empty space a baseline temperature of about 2.7 Kelvin. But in laboratories, using techniques like laser cooling and evaporative cooling, scientists have cooled atoms to temperatures far colder, measured in nanokelvins, sometimes even picokelvins. At these extreme temperatures, matter enters exotic states. Bose-Einstein condensates form, where atoms lose individual identity and behave as a single quantum entity. Quantum effects become visible at macroscopic scales. Strange phenomena emerge that exist nowhere else in the natural universe. Why bother creating such extreme cold? Partly to study quantum mechanics. At normal temperatures, thermal motion obscures quantum effects. But cool atoms enough, and quantum behavior dominates. Scientists can observe and manipulate quantum states with precision impossible at higher temperatures. These ultra-cold systems also have practical applications. In atomic clocks that measure time with extraordinary accuracy, in quantum computers, in sensors that detect the tiniest gravitational variations. It's remarkable that achieving the universe's coldest temperatures requires tremendous effort and sophisticated technology. Natural processes throughout the cosmos never reach these extremes. We had to build equipment, refine techniques, and carefully control conditions to create temperatures nature never produces on its own. In a sense, we've pushed beyond what the universe naturally achieves. We've created conditions more extreme than anything found in nature, at least in this regard. It's a small triumph, making the coldest place in existence through human ingenuity and curiosity. Imagine throwing a ball at a wall. If you don't throw it hard enough, it bounces back. It doesn't have enough energy to pass through. This is how classical physics works. Energy barriers are absolute. But quantum mechanics permits something stranger: tunneling. A particle encountering a barrier it doesn't have enough energy to overcome can sometimes appear on the other side anyway, as if it passed through solid matter like a ghost. This happens because particles aren't really particles in the classical sense. They're waves of probability, and waves don't stop abruptly at barriers. They decay exponentially into forbidden regions. Usually this decay is so rapid that the probability of finding the particle on the far side is essentially zero. But for thin enough barriers and light enough particles, there's a small but real chance the particle tunnels through. This isn't theoretical speculation. Tunneling is essential to how the universe works. It's how the sun shines. In the solar core, hydrogen nuclei must overcome enormous electromagnetic repulsion to get close enough to fuse. Classically, they don't have enough energy, but quantum tunneling allows some nuclei to pass through this energy barrier, enabling fusion reactions that power the sun. Tunneling also enables technologies we use daily. Scanning tunneling microscopes image individual atoms by measuring tunneling currents. Flash memory in computers relies on electrons tunneling through thin oxide barriers. Radioactive decay, alpha particles escaping atomic nuclei, happens through tunneling. It's one of quantum mechanics' most counterintuitive features. Barriers aren't absolute. The forbidden can sometimes happen. Energy requirements can be violated, temporarily. The universe at quantum scales permits possibilities that classical physics denies. And perhaps there's something poetic about that. The idea that barriers, even seemingly insurmountable ones, are not quite as solid as they appear. Quantum mechanics builds in a small probability of the impossible, a chance for nature to surprise us. Schrödinger's cat is perhaps the most famous thought experiment in physics. A cat is placed in a sealed box with a device that has a 50% chance of releasing poison. According to quantum mechanics, until you open the box and observe, the system exists in superposition. The cat is simultaneously alive and dead. This sounds absurd. Cats are clearly either alive or dead, not both. And that's exactly Schrödinger's point. He proposed this scenario in 1935 not to illustrate how quantum mechanics works, but to show how ridiculous it seems when applied to everyday objects. At the quantum level, superposition is real. A particle can be in multiple states simultaneously, spin up and spin down here and there, until measured. Observation collapses the superposition into one definite outcome. But where does this quantum behavior stop and classical behavior begin? Can a large, complex system like a cat truly be in superposition? Most interpretations of quantum mechanics say no, not practically. The cat interacts with air molecules, photons, its own body heat. These interactions constitute measurement, collapsing the superposition almost instantly. Decoherence happens so fast for macroscopic objects that superposition never survives long enough to observe. But the question remains philosophically troubling. What counts as observation? Does it require consciousness? Or is any interaction sufficient? Different interpretations give different answers. The cat serves as a boundary marker, showing where quantum weirdness meets everyday reality. We accept superposition for electrons, but balk at dead and alive cats. Somewhere between those scales, the rules change, or seem to. Understanding exactly how and why remains one of physics' deepest puzzles. The cat, neither alive nor dead but questioning, haunts the foundations of quantum mechanics still. What we call empty space, the vacuum, isn't empty at all. According to quantum field theory, it seethes with activity. Virtual particles constantly pop into existence in particle-antiparticle pairs, exist for impossibly brief moments, then annihilate back into nothingness. These aren't real particles in the usual sense. They exist only briefly, borrowing energy from the quantum vacuum in a way permitted by the Heisenberg uncertainty principle. The principle says that over very short time scales, energy can fluctuate. Virtual particles exploit this loophole, appearing momentarily before disappearing. This sounds like abstract theory, but it has measurable consequences. The Casimir effect demonstrates vacuum fluctuations directly. Place two uncharged metal plates very close, together in a vacuum. Fewer virtual particles can exist between the plates than outside them. The space is too constrained. This creates a pressure difference, pushing the plates together with measurable force. Scientists have measured this force. It's real. The quantum vacuum has structure, energy, physical effects. These fluctuations might also explain dark energy, the mysterious force accelerating the universe's expansion. Perhaps the vacuum energy from quantum fluctuations creates a baseline pressure throughout space, driving expansion. The numbers don't match perfectly. In fact, they're off by an enormous factor. But the principle might be right. Empty space, viewed quantum mechanically, is a churning sea of temporary existence, particles flickering in and out of reality too quickly to observe directly, but leaving measurable traces. The vacuum has energy, structure, activity. Nothingness is full of something. It changes how we think about existence itself. Even in the absence of matter, of energy, of anything we'd normally call real, the fabric of space maintains this baseline activity, this fundamental quantum restlessness that never settles into true emptiness. Black holes warp space-time so severely that near the event horizon, time dilation becomes extreme. If you fell toward a black hole while someone watched from a safe distance, they'd see you slow down, approaching the horizon asymptotically, never quite crossing, frozen in time from their perspective. But from your perspective, falling inward, time continues normally for you. What changes is your view of the outside universe. Looking back toward normal space, you'd see time accelerate. Clocks would tick faster. Stars would age. The universe's future would unfold before you at an accelerating rate. Close enough to the event horizon, this effect becomes dramatic. You could watch billions of years pass in the outside universe in what feels like moments. If you could somehow hover at the horizon indefinitely, impossible practically, but hypothetically, you'd see the entire remaining future of the observable universe flash past. Galaxies colliding, stars dying, the cosmic background radiation cooling toward absolute zero, perhaps the eventual heat death of the universe. Of course, you wouldn't actually survive. Tidal forces near stellar mass black holes would tear you apart, and even near supermassive black holes, where tidal forces are gentler, you'd eventually cross the horizon and be unable to escape, crushed at the singularity. But the thought experiment reveals something profound about the relationship between gravity and time. Strong gravitational fields don't just pull on matter, they stretch time itself. Near a black hole, your time and the universe's time diverge so dramatically that you could theoretically witness cosmic epochs unfold while experiencing only moments. It's relativity's most extreme prediction about time, pushed to limits where space-time curves back on itself, where the distinction between past and future becomes strange and malleable. There's a fundamental limit to what we can know about the quantum world. The Heisenberg uncertainty principle states that the more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. It's not a limitation of our instruments. It's built into the nature of reality. This happens because particles are also waves. Position and momentum are related to different properties of waves. Position to where the wave is localized, momentum to its wavelength. You can't have a wave that's perfectly localized in space, definite position, and also has a single definite wavelength, definite momentum. The two properties are complementary, like trying to pinpoint a single moment in a musical note. You lose information about its pitch. Mathematically, the uncertainty in position times the uncertainty in momentum must be at least as large as Planck's constant divided by 4p. This is an incredibly small number, which is why we don't notice quantum uncertainty in everyday life. But at atomic scales, it's significant. The uncertainty principle has profound implications. It means electrons can't have definite orbits around nuclei. They exist in fuzzy orbitals. It permits quantum tunneling. It's why atoms don't collapse. Electrons can't be pinned to exact positions and momentums that would allow them to spiral into the nucleus. It also means the vacuum can't be perfectly empty. Even with no particles present, there must be fluctuations. The uncertainty principle forbids perfect stillness, perfect zero energy. The quantum world maintains irreducible uncertainty, a fuzziness that can never be eliminated. Perhaps this makes the universe more interesting. Perfect knowledge would mean perfect predictability, a clockwork cosmos where everything is determined. Uncertainty preserves possibility, keeps the future genuinely open, maintains mystery at the foundation of existence. For every particle, there's an antimatter counterpart, identical except for opposite charge. Electrons have positrons, protons have antiprotons. When matter and antimatter meet, they annihilate completely, converting their entire mass into pure energy. This is E or mc2 at maximum efficiency. Chemical reactions release a tiny fraction of mass as energy. Nuclear fission releases about 0.1% of mass. But matter-antimatter annihilation converts 100% of mass into energy, the ultimate in energy extraction. A gram of antimatter annihilating with a gram of matter would release energy equivalent to a 43 kiloton nuclear bomb. It's the most energy-dense reaction possible. Antimatter isn't science fiction. We create it routinely in particle accelerators. Positron emission tomography, PET, scans use positrons from radioactive decay. lightning produces small amounts of antimatter. Some radioactive isotopes emit positrons naturally. The puzzle is why our universe contains far more matter than antimatter. The Big Bang should have produced them in equal amounts. They should have annihilated, leaving only energy. Yet here we are, made of matter, in a universe dominated by matter. There must be some asymmetry, some physical process that favored matter over antimatter very slightly. Perhaps one extra matter particle for every billion matter-antimatter pairs. Those pairs annihilated, and the tiny excess became everything we see, every star, planet, and atom. We don't fully understand this asymmetry. It's one of cosmology's great mysteries. Why does matter exist at all? Why didn't everything annihilate into photons in the first moments after the Big Bang? Whatever the answer, we're fortunate it happened. Without that tiny imbalance favoring matter, the universe would be dark, empty, just radiation expanding forever with nothing solid, nothing complex, nothing alive. Place two uncharged, perfectly conducting metal plates very close together in a vacuum. They'll attract each other. Not through electromagnetism, they're neutral. Not through gravity, they're too light. Through the Casimir effect, a force arising from quantum vacuum fluctuations. Here's how it works. Even in vacuum, quantum field theory says virtual particles constantly appear and disappear. Between the plates, only virtual particles with wavelengths that fit exactly in the gap can exist. Outside the plates, all wavelengths are possible. This means there are more virtual particles pushing from outside than inside, creating net pressure that pushes the plates together. The closer the plates, the stronger the effect. In 1948, Dutch physicist Hendrik Casimir predicted this. In 1997, it was measured precisely. The force is tiny, measurable only at distances of micrometers or less, but real. It's perhaps the most direct evidence of quantum vacuum fluctuations. Something observable emerges from nothing, from the baseline quantum activity of empty space. The Casimir effect has practical implications in nanotechnology, where it can cause microscopic components to stick together unexpectedly. Engineers designing tiny machines must account for it. But philosophically, it's profound. It demonstrates that vacuum isn't absence. It's presence of quantum fields in their lowest energy state, still active, still capable of producing forces and effects. Nothing is not nothing. The deepest emptiness we can achieve still seethes with quantum activity, still contains structure and energy. True nothingness, absolute absence of everything, including quantum fields, may not even be a meaningful concept in our universe. The Casimir effect proves that even in perfect vacuum, the universe isn't empty. It's full of potential, of fluctuations, of forces arising from the fundamental quantum nature of reality itself. If you could travel at near light speed, the universe would transform. Space itself would compress in your direction of motion, a phenomenon called length contraction. The faster you go, the more dramatic the compression. At 90% of light speed, distances ahead would compress to about 44% of their rest length. At 99.9% light speed, they'd shrink to about 4.5%. Approach light speed closely enough, and the journey to distant stars could theoretically be completed in subjectively short times, even though light years of distance separate you from your destination. This isn't an illusion or measurement artifact. Space genuinely contracts in the direction of motion from the perspective of the moving observer. A galaxy that's 100,000 light-years across at rest would appear compressed to a thin disk if you flew toward it at 99.9999% light speed. This allows for a kind of loophole in interstellar travel. Yes, nothing can exceed light speed. But length contraction means that from your perspective, distances shrink. You could cross the galaxy in subjectively reasonable time if you could reach speeds close enough to light, though billions of years would pass on Earth. The catch is acceleration. Reaching these speeds requires enormous energy, approaching infinity as you near light speed. And if you somehow achieved it, returning home would mean finding an Earth billions of years older, everyone you knew long dead, civilization transformed beyond recognition. Length contraction pairs with time dilation. They're two aspects of the same relativistic effect. As you move faster, time slows for you and space compresses ahead of you. The universe reshapes itself around your motion, maintaining the cosmic speed limit while allowing journeys that would otherwise take impossibly long. When you measure a quantum system in superposition, say an electron that could be spin up or spin down, you observe one definite outcome. But according to the many worlds interpretation, both outcomes occur. The universe splits. One branch contains you observing spin up. Another branch contains you observing spin down. This interpretation, proposed by Hugh Everett in 1957, takes quantum mechanics literally. Superposition never actually collapses. Instead, all possibilities happen, each in its own branch of reality. You only experience one branch because you split two. There's a version of you in each outcome. It sounds like science fiction, but it's a serious interpretation held by many physicists. It solves certain problems with standard quantum mechanics, particularly the measurement problem, why observation seems to collapse superpositions. In many worlds, there's no collapse. The universe evolves deterministically according to the Schrödinger equation. What seems like collapse is just you becoming entangled with the system, your consciousness following one branch, while other versions of you follow other branches. If true, reality is constantly branching. Every quantum event, and there are countless per second, creates new universes. The number of parallel worlds grows exponentially, encompassing every possible history, consistent with quantum mechanics. This means somewhere in the multiverse, every possible version of your life exists. Versions where you made different choices, where quantum events fell differently, where history diverged in large and small ways. Can we ever know if this is true? Probably not directly. The other branches are causally isolated. We can't interact with them or detect them. Many worlds makes the same predictions as other interpretations for any measurable experiment. But it offers a perspective. Perhaps the quantum randomness we observe reflects not chance, but reality's fullness. All possibilities realized across infinite parallel worlds. Classical computers process information using bits, units that are either 0 or 1. Quantum computers use qubits, quantum bits that can be 0, 1, or both simultaneously through superposition. This allows quantum computers to explore many possibilities at once. For certain problems, this creates exponential speedup. A calculation that would take a classical computer millions of years could potentially take a quantum computer hours. For example, factoring large numbers, the basis of much modern encryption, is very hard for classical computers. Breaking RSA encryption requires factoring numbers hundreds of digits long, which is practically impossible. But quantum computers running Shor's algorithm could do it relatively easily, threatening current cryptographic systems. Quantum computers could also simulate quantum systems, molecules, materials, chemical reactions, far more efficiently than classical computers. This could revolutionize drug discovery, materials science, and our understanding of quantum phenomena. But there are enormous challenges. Qubits are fragile. They must be isolated from environmental interactions that cause decoherence, the loss of quantum properties. Maintaining quantum coherence long enough to perform useful calculations requires extreme conditions, near absolute zero temperatures, careful shielding from vibrations, and electromagnetic interference. Current quantum computers have tens to hundreds of qubits. Useful quantum computers for most applications would need thousands or millions. The engineering challenges are staggering. Still, progress continues. Quantum computers are transitioning from theoretical possibilities to working prototypes. They won't replace classical computers. They're not better at everything, just at specific quantum-sensitive problems. But for those problems, they could be transformative. We're at the beginning of quantum computing, much like the 1950s were for classical computing. The full impact remains unknown, but the potential is extraordinary, using quantum mechanics not just to observe the universe, but to compute with its fundamental properties. Light is both wave and particle, not sometimes one and sometimes the other, both, simultaneously, always. Which aspect you observe depends on how you look. Shine light through two slits, and it creates an interference pattern, alternating bright and dark bands characteristic of waves. The peaks and troughs of light waves from each slit overlap, reinforcing in some places, canceling in others. Pure wave behavior. But detect light with a sensor, and it arrives in discrete packets, photons, individual clicks, countable particles. Each photon carries specific energy determined by its frequency, pure particle behavior. This duality isn't unique to light. Electrons, atoms, even molecules show it. Send electrons through double slits one at a time, and they still create interference patterns, as if each electron passes through both slits and interferes with itself. But detect which slit it passes through, and the interference disappears. It behaves like a particle. Niels Bohr called this complementarity. Wave and particle aren't contradictory descriptions. They're complementary aspects of quantum reality. Which aspect manifests depends on what question you ask, what measurement you make. We want nature to be one thing or the other, waves or particles. Our classical intuition demands it, but nature refuses. At quantum scales, reality is inherently dual, irreducibly both wave-like and particle-like, revealing different faces depending on how we interact with it. Perhaps this tells us something important. Maybe our categories, wave, particle, even the distinction between them, are human constructs imposed on a reality that doesn't naturally divide that way. Maybe nature is fundamentally something else, something we don't have words for, and wave and particle are just partial glimpses, limited perspectives on a deeper truth. Light doesn't choose. It is what it is. We're the ones insisting it must be categorized, forcing it into familiar concepts. And light, patient and strange, reveals whichever aspect we're equipped to see. Before Einstein, space and time were separate. Space was the stage where events occurred. Time was the universal clock ticking uniformly for everyone. They were independent, absolute, unchanging. Einstein's relativity shattered this. Space and time are connected, interwoven into a single four-dimensional fabric called space-time. You can't change your motion through space without changing your motion through time. They're coupled, trading off. Move faster through space, move slower through time. This isn't metaphorical. Space-time is as real as space alone ever was. More real, actually, since space and time separately are reference frame dependent. Different observers moving relative to each other disagree about distances and durations, but agree on space-time intervals, which combine spatial and temporal separations. Gravity, in Einstein's theory, isn't a force pulling objects together. It's the curvature of space-time. Mass and energy curve the fabric around them, creating valleys and hills. Objects follow the straightest paths they can through this curved geometry, which we perceive as gravitational attraction. Earth orbits the sun not because the sun pulls on it, but because the sun's mass curves space-time, and Earth follows that curvature. The moon orbits Earth the same way. Even light bends near massive objects, following curved space-time paths. This curvature is dynamic. Massive objects moving and accelerating create ripples, gravitational waves, that propagate through space-time at light speed. The fabric itself can vibrate, carry information, stretch and compress. Thinking in space-time rather than separate space and time resolves paradoxes in relativity. Events that seem simultaneous to one observer aren't to another. The now that seems universal is actually a slicing of space-time that depends on your motion. We're not moving through time. We're moving through space-time, tracing paths called world lines. Every object's history is a curve through 4 dimensions. And everything that ever was or will be already exists in the space-time manifold, laid out eternally in the block universe, some interpretations suggest. Quantum entanglement creates perfect correlations between particles across any distance. Measure one, and you instantly know what measuring the other will yield. But, crucially, you can't use this to send information faster than light. Here's why. When you measure an entangled particle, you get a random result. You can't control what you'll find. The outcome is genuinely random until measurement occurs. Only afterward, when you compare your results with measurements on the partner particle, do you discover the correlation. So if you're trying to send a message, you measure your particle, get a random result, and the person at the other end measures theirs and also gets a random result. They don't know what you got, and you don't know what they got until you communicate through normal channels, light speed limited channels like radio or phones. The entanglement ensures the results are correlated, but neither party can see that correlation without classical communication. You can't encode a message in your measurement results because you don't control them. They're random. This preserves causality. If entanglement allowed faster than light communication, it would permit paradoxes, sending messages to your own past, creating logical contradictions. The randomness of quantum measurements prevents this. But the correlations themselves are instantaneous and perfect. The universe somehow maintains these connections across space without transmitting information through the intervening distance. It's non-local correlation without causal influence. Einstein called it spooky action at a distance because it bothered him deeply. But experiments confirm it repeatedly. Nature permits these strange correlations while preserving causality and the light speed limit. It's a delicate balance. the universe allows quantum weirdness, instantaneous correlations, superposition, entanglement, while preventing violations of relativity's fundamental principles. Randomness is the key that makes it work, preserving both quantum mechanics and cosmic speed limits. Why doesn't your hand pass through the table when you press down? The usual answer is electromagnetic repulsion between atoms, but there's something deeper: the Pauli exclusion principle. This quantum mechanical principle states that no two fermions, particles like electrons, protons, neutrons, can occupy the same quantum state simultaneously. Each electron in an atom must have a unique set of quantum numbers. They can't all collapse into the lowest energy state. This creates the shell structure of atoms. The first electron occupies the lowest energy orbital. The second must go into a slightly different state, opposite spin, perhaps. The third must find another unique state, typically in a higher orbital, and so on. Electrons stack up, filling progressively higher energy levels because they can't all crowd into the ground state. This exclusion principle creates what's called degeneracy pressure. In normal matter, when atoms are pushed together, their electron clouds resist overlapping because electrons in one atom can't occupy the same states as electrons in another. This resistance, degeneracy pressure, makes solid matter solid. In more extreme conditions, degeneracy pressure becomes dramatic. In white dwarf stars, electron degeneracy pressure supports the star against gravity. In neutron stars, it's neutron degeneracy pressure. Without the Pauli principle, all these structures would collapse. The principle also explains chemistry. Different elements have different properties because electrons must fill orbitals in specific ways. Valence electrons, those in the outermost shells, determine chemical behavior. The entire periodic table, all of chemistry, emerges from the Pauli principle, forcing electrons into specific configurations. So solid matter is solid not just because of forces, but because of a fundamental quantum rule that prevents particles from occupying identical states. Reality has structure because nature enforces uniqueness at the quantum level, maintaining distinctions that classical physics wouldn't require. Your phone's GPS works because of Einstein's relativity, both special and general. Without relativistic corrections, GPS would accumulate errors of about 10 kilometers per day, making it essentially useless. GPS satellites orbit about 20,000 kilometers above Earth, traveling at roughly 14,000 kilometers per hour. Two relativistic effects matter. First, special relativity. Because the satellites are moving, their clocks tick slower than clocks on Earth's surface by about 7 microseconds per day. This is velocity-based time dilation. Second, general relativity. The satellites are in weaker gravity than Earth's surface, so their clocks tick faster by about 45 microseconds per day. This is gravitational time dilation. The gravitational effect dominates. Net result: satellite clocks run about 38 microseconds per day faster than ground clocks. This sounds tiny, but GPS works by timing radio signals, traveling at light speed. Light travels about 30 centimeters per nanosecond. A 38 microsecond error translates to about 11 kilometers, completely unacceptable for navigation. So GPS satellites have their clocks adjusted before launch, set to run slightly slow, so that once in orbit, relativistic effects bring them into sync with ground clocks. The system continuously monitors and corrects for relativistic and other effects. It's a beautiful confirmation of relativity in everyday technology. Every time you use GPS, navigating, ordering a rideshare, checking a map, you're relying on Einstein's century-old predictions about space, time, and gravity. Relativity isn't abstract theory anymore. It's engineering necessity. It's embedded in infrastructure we take for granted. The universe's fundamental structure, the way time flows differently in different gravitational fields and at different velocities, shapes the technology in your pocket. Watch a pot closely enough and it won't boil. Not metaphorically. In quantum mechanics, continuous observation can actually prevent change. This is the quantum Zeno effect, named after Zeno's paradox about arrows that never reach their targets. In quantum mechanics, systems evolve through superpositions, gradually transitioning from one state to another. But measurement collapses superposition, forcing the system into a definite state. If you measure frequently enough, you keep collapsing the system back before it has time to evolve, effectively freezing it in place. Imagine a particle that has a small chance of decaying each second. If you don't observe it, quantum mechanics describes it as gradually evolving into a superposition of decayed and undecayed states. After enough time, measurement will probably find it decayed, but if you observe every microsecond, you keep collapsing the superposition before significant decay probability accumulates. The particle keeps getting reset to not yet decayed. Observation prevents the decay, not by physically stopping it, but by repeatedly resetting the quantum state. This has been demonstrated experimentally with atoms and other quantum systems. Frequent measurements can inhibit transitions that would otherwise occur. The effect has potential applications in quantum computing, where maintaining quantum states against decoherence is critical. Perhaps strategic measurements could protect quantum information, freezing unwanted transitions while allowing desired operations. But it's also philosophically intriguing. It suggests observation isn't passive. It actively shapes reality at quantum scales. The universe doesn't evolve independently of measurement. Measurement is participation, affecting outcomes through the act of witnessing. In some sense, the quantum Zeno effect makes literal the idea that a watched pot never boils. Watch closely enough, constantly enough, and quantum change ceases, frozen by observation's repeated intervention. Black holes aren't entirely black. Stephen Hawking showed in 1974 that quantum effects near the event horizon cause black holes to emit radiation, slowly losing mass over time. Here's the mechanism. Vacuum fluctuations near the horizon create virtual particle pairs. Normally, they'd annihilate almost immediately, but if one falls into the black hole while the other escapes, the escaping particle becomes real, carrying away energy. From outside, this appears as thermal radiation emitted by the black hole, Hawking radiation. The black hole loses the mass energy equivalent of the escaped particle. For stellar mass black holes, this radiation is incredibly faint, colder than the cosmic microwave background. They gain more energy from absorbing background radiation than they lose to Hawking radiation. They grow, not shrink. But far in the future, when the universe has expanded and cooled, when stars have burned out and the cosmic background has faded, black holes will begin to evaporate noticeably. The process is slow. A solar mass black hole would take about 1067 years to evaporate completely. Supermassive black holes take even longer, 100 years or more. These timescales dwarf the current age of the universe by unimaginable factors, But eventually, if Hawking is correct, every black hole will evaporate, ending its existence not with violence, but with a gradual fade into nothingness, possibly ending in a final burst of radiation as the last mass disappears. This prediction has never been observed. Hawking radiation is far too weak to detect from actual black holes, but it's a profound theoretical insight, connecting quantum mechanics, thermodynamics, and general relativity, showing that even black holes aren't eternal, that even the darkest objects in the universe eventually return their energy to the void. Electrons, protons, and many other particles have a property called spin, but they're not actually spinning, at least not in any classical sense. Spin is a purely quantum mechanical property with no real equivalent in everyday physics. If you imagine an electron as a tiny sphere rotating on its axis, the math doesn't work. To generate the magnetic field associated with its spin, the electron's surface would have to move faster than light. That's impossible, which tells us the classical picture is wrong. Spin is better understood as an intrinsic form of angular momentum, a fundamental property particles possess, like mass or charge, not arising from actual rotation, but existing inherently. Electrons can be spin up or spin down along any chosen axis. Measuring spin along one axis gives a definite result, but the spin along perpendicular axes becomes uncertain. It's inherently quantum, discrete values, superposition, measurement affecting the state. Spin has practical importance. It's responsible for magnetism. The Pauli exclusion principle depends on spin. Two electrons can occupy the same orbital only if they have opposite spins. Spin is exploited in technologies like magnetic resonance imaging, MRI, and emerging quantum computers. But fundamentally, spin represents something the classical world doesn't contain: an intrinsic angular momentum unconnected to motion. Particles have spin even when stationary. It's built into their quantum nature. Perhaps this is a reminder of how different the quantum world truly is. We use familiar words: spin, wave, particle, but they're metaphors, approximations. The quantum realm operates on principles our everyday experience never prepared us for. Electrons have spin, but they're not spinning. They're doing something quantum mechanics describes mathematically, but that doesn't translate cleanly into classical imagery. We live in a universe stranger than our language can fully capture. If quantum mechanics permits superposition, entanglement, and all the weirdness we've discussed, why don't we see it in everyday life? Why aren't cats both alive and dead, or chairs in superposition of locations? The answer is decoherence. Macroscopic objects constantly interact with their environment: air molecules, photons, vibrations, heat. These interactions entangle the object with its surroundings, rapidly destroying quantum coherence. Imagine a dust particle in superposition of two locations. Air molecules bounce off it constantly. If the particle is in location A, molecules bounce one way. If it's in location B, they bounce differently. The molecules become entangled with the particle's position, carrying information into the environment. This happens almost instantaneously for anything larger than atoms. Within fractions of a second, often far faster, the quantum superposition effectively collapses as information spreads irreversibly into the environment. The system becomes classical, definite, localized, no longer in superposition. This isn't true collapse. From a many worlds perspective, all branches still exist, but they become so thoroughly separated and isolated by environmental entanglement that interference between them becomes impossible. Practically, the system behaves classically. Decoherence explains the quantum classical boundary. It's not that quantum mechanics stops applying to large objects. It's that large objects can't maintain coherence long enough for us to observe quantum behavior. They interact too much, too quickly. Quantum computers fight decoherence constantly, isolating qubits, cooling them, shielding them from vibrations and electromagnetic noise. Maintaining quantum coherence even briefly requires extraordinary effort. In a sense, the classical world emerges from quantum foundations through decoherence. The apparent solidity and definiteness of everyday reality is an approximation, valid because quantum coherence vanishes so quickly for macroscopic objects that we never see the underlying quantum fuzz. In 1964, physicist John Bell proved something remarkable. If quantum mechanics is correct, the universe must either allow instantaneous influences across distance or abandon the idea that particles have definite properties before measurement. Classical intuition suggests particles have real, definite properties, independent of observation. An electron has a position and momentum whether you measure them or not. And local realism says that measuring one particle can't instantly affect another far away. Information can't travel faster than light. Bell showed these assumptions are incompatible with quantum predictions. He derived mathematical inequalities that any local realistic theory must satisfy. Then he showed quantum mechanics violates these inequalities, predicting stronger correlations between entangled particles than local realism allows. Experiments confirmed Bell's predictions. Nature violates Bell's inequalities. The classical assumptions fail. This forces a choice. Either quantum mechanics is non-local, measurement of one particle instantly affects its entangled partner, or particles don't have definite properties before measurement. Reality depends on observation in some fundamental way. Most physicists accept non-locality. Entangled particles maintain correlations across any distance, seemingly violating locality. But as discussed earlier, this can't transmit information, so causality remains intact. Others question realism itself, accepting that particles simply don't have definite values until measured. Properties emerge through measurement rather than being revealed by it. Either way, Bell's theorem shows our classical intuitions about reality, that things have definite properties independent of us, and that influences can't exceed light speed. Can't both be true? Nature is fundamentally stranger than common sense suggests. It's one of the most profound results in physics, proving that quantum weirdness isn't just interpretation or philosophical speculation. The universe demonstrably behaves in ways that violate our deepest assumptions about how reality should work. Most of the matter in the universe is invisible. We call it dark matter, and it makes up roughly 85% of all matter. Yet we've never directly detected a single particle of it. We know it exists only through its gravitational effects. Galaxies rotate too fast. Stars at the edges should fly off into space based on the visible matter we see. But they don't. Something invisible is holding them together. Extra mass we can't see, creating gravitational pull that keeps galaxies intact. Galaxy clusters show the same pattern. They contain more mass than their visible stars, and gas can account for. Gravitational lensing, the bending of light around massive objects, reveals invisible mass distributions. Computer simulations of the universe's evolution only match observations when they include vast amounts of dark matter. But what is it? We don't know. It doesn't emit, absorb, or reflect light. It doesn't interact electromagnetically. It barely interacts with normal matter at all, except through gravity. Particles of dark matter might be passing through you right now, billions of them per second, without touching a single atom. Scientists have proposed many candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; even primordial black holes. Detectors buried deep underground wait in darkness, hoping to catch a rare interaction between dark matter and ordinary atoms. So far, nothing definitive. It's humbling. The universe is made mostly of something we can't see, can't touch, can barely detect. Normal matter, atoms, stars, planets, everything we've ever observed directly, is just a small fraction of what exists. We live in a cosmos dominated by invisible scaffolding, material that shapes the structure of everything, but remains profoundly mysterious. Perhaps dark matter will be the great discovery of this century, or perhaps it will remain elusive longer, a ghost haunting the equations, bending light, holding galaxies together, but never quite revealing itself. The universe isn't just expanding, it's accelerating. Galaxies are moving apart faster now than they were billions of years ago. Something is driving this acceleration, and we call it dark energy, though we have almost no idea what it actually is. This discovery in 1998 shocked cosmologists. They expected expansion to slow down over time, gravity gradually pulling everything back together. Instead, observations of distant supernovae showed expansion speeding up. Dark energy comprises roughly 68% of the universe's total energy. It behaves unlike anything familiar, a kind of energy inherent to space itself, creating repulsive pressure that pushes everything apart. The more space expands, the more dark energy appears, driving further expansion in a runaway feedback loop. If dark energy remains constant or strengthens, the universe's fate is cold and dark. Galaxies beyond our local group will eventually recede faster than light can travel, disappearing beyond our cosmic horizon. In trillions of years, future astronomers might see only their own galaxy surrounded by darkness, with no evidence other galaxies ever existed. If dark energy strengthens dramatically, the Big Rip becomes possible, expansion accelerating so violently that it eventually tears apart galaxy clusters, then galaxies, then solar systems, then planets, atoms, everything, in a catastrophic unraveling of all structure. But we don't know if dark energy is truly constant. We call it the cosmological constant, but that's more description than explanation. It might be vacuum energy, a property of empty space. It might be a dynamic field that changes over time. We measure its effects but don't understand its nature. Most of the universe, dark matter and dark energy combined, remains mysterious. We've mapped only the 5% that's normal matter. The rest is darkness, question marks, placeholders in equations waiting for understanding. There might be a smallest possible distance, a fundamental limit below which the concept of space itself breaks down. We call it the Planck length, approximately 10^35 meters, incomprehensibly tiny. To give perspective, if you enlarged an atom to the size of the observable universe, the Planck length would be about the size of a tree. It's 20 orders of magnitude smaller than a proton. At this scale, quantum mechanics and gravity collide. Quantum uncertainty means particles' positions become fuzzy. Gravitational effects mean tiny fluctuations in mass energy create significant space-time curvature. At the Planck scale, space-time itself might become granular, foamy, discontinuous. No longer a smooth fabric, but something discrete, quantized, fundamentally uncertain. We don't have a theory of quantum gravity that fully describes physics at this scale. General relativity and quantum mechanics both work brilliantly in their respective domains, but contradict each other at Planck scales. We need a unified theory, string theory, loop quantum gravity, or something yet undiscovered to understand what happens here. Some theories suggest space-time emerges from something more fundamental, like information or quantum entanglement. Space might not be continuous but made of discrete units, Planck-sized pixels of reality. If true, zooming in eventually reaches a limit. Below the Planck length, smaller might not mean anything. Questions like, where exactly is this particle, might lack answers, not because we can't measure precisely enough, but because reality itself doesn't define positions more finely. It's the ultimate boundary, not a barrier we can't cross technologically, but a conceptual limit where our most fundamental categories, like space and distance, might dissolve into something stranger, something our current physics can't quite describe. The Planck length marks the edge of known physics, the frontier where understanding gives way to mystery. Quantum mechanics is fantastically successful. It predicts experimental results with extraordinary precision. Yet we still don't truly understand how it works. Specifically, we don't understand measurement. Before measurement, quantum systems exist in superposition, multiple states simultaneously. Schrödinger's equation describes this evolution perfectly, deterministically. Then measurement happens and superposition collapses into one definite outcome. The randomness of quantum mechanics emerges here, in this collapse. But what causes collapse? Schrödinger's equation doesn't include it. The equation predicts continuous superposition forever. Collapse is added separately, as a postulate, without explanation. What counts as measurement? Does it require consciousness, a scientific instrument, any interaction? Where exactly does the quantum world end and the classical world begin? Different interpretations give different answers. Copenhagen says measurement causes collapse, but doesn't. Explain the mechanism. Many Worlds says there's no collapse. All outcomes occur in separate branches. Pilot wave theory says particles always have definite positions guided by quantum waves. Each interpretation has strengths and problems. A century after quantum mechanics formulation, we still debate these fundamental questions. We can calculate probabilities, predict experiments, build quantum computers, but we can't agree on what's actually happening. Some physicists say this is fine. Quantum mechanics is a calculation tool, and demanding deeper explanation is metaphysics, not physics. Others insist we must understand what measurement means, what reality is like when we're not looking, how the quantum gives way to the classical. The measurement problem remains open, perhaps the deepest mystery in physics. We have the most successful theory ever created, yet we disagree about what it tells us about reality. The equations work. The meaning remains elusive. The fundamental constants of physics, the strength of gravity, the electromagnetic force, the mass of electrons, seem precisely tuned for life's existence. Change them even slightly, and the universe becomes inhospitable. If gravity were slightly stronger, stars would burn too fast, dying before life could evolve. Slightly weaker, and stars wouldn't form at all. If the electromagnetic force differed by a few percent, chemistry as we know it couldn't exist. Carbon, essential for life, requires incredibly specific nuclear resonances to form in stars. These aren't minor adjustments. The cosmological constant, related to dark energy, seems fine-tuned to 1 part in 10^120. If it were slightly larger, the universe would have expanded too fast for galaxies to form. Slightly smaller and negative, and the universe would have collapsed immediately after the Big Bang. This raises profound questions. Why do these constants have the values they do? Is it coincidence, design, necessity? One answer is the anthropic principle. We observe these values because only universes with these values produce observers. In universes with different constants, no one exists to ask why. Another answer is the multiverse. Perhaps countless universes exist with different constants. Most are barren. We inhabit one of the rare ones capable of supporting life, because that's the only kind we could inhabit. It's selection bias on a cosmic scale. Or perhaps deeper physics we don't understand constrains these constants. Maybe they're not arbitrary but determined by some unified theory that makes our values inevitable. The fine-tuning problem doesn't prove anything definitive, but it asks uncomfortable questions about why the universe seems so remarkably suited for our existence, why the constants balance on knife edges that permit complexity, structure, chemistry, life. The holographic principle is one of physics' strangest ideas. All the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary, like a hologram stores 3D images on flat film. This emerged from studying black holes. Black hole entropy, a measure of information content, depends on the event horizon's surface area, not its volume. This suggests the information inside is somehow stored on the surface. Physicists generalize this. Perhaps all of space works this way. Everything happening in 3 dimensions might be encoded on a 2-dimensional boundary, possibly infinitely far away. Our 3D reality could be a projection, a hologram of information stored on a distant surface. This sounds like metaphysics, but it's serious theoretical physics. The ADS-CFT correspondence, a duality between certain types of space-time and quantum field theories on their boundaries, provides mathematical support. Information in the bulk space corresponds exactly to information on the boundary. What does this mean for reality? It's unclear. If the holographic principle is fundamental, space itself might be emergent, not fundamental. The 3 dimensions we experience could arise from more basic processes occurring on a lower dimensional structure. Some theories suggest our universe's boundary might be at the cosmic horizon, with all information encoded there. We experience 3 dimensions, but fundamentally, reality might be 2-dimensional, with the 3rd dimension emerging holographically. This challenges our intuitions profoundly. We trust that 3-dimensional space is real, fundamental, but perhaps it's derived secondary, a convenient description of something more basic. Perhaps the universe is like a hologram, appearing 3-dimensional but fundamentally encoded on a surface. Reality might have fewer dimensions than we experience, with our familiar space being an elaborate projection. If dark energy strengthens over time, the universe might end in the Big Rip, a catastrophic tearing apart of all structure. Currently, dark energy drives expansion, but doesn't affect bound systems. Galaxies, solar systems, atoms, they're held together by forces stronger than the expansion of space. But if dark energy intensifies, eventually it overcomes everything. The timeline might look like this. In 20 billion years, galaxies begin tearing apart, stars unbound from each other. In 22 billion years, solar systems disintegrate, planets rip from their orbits. Months before the end, stars themselves shred. Minutes before, planets explode. In the final fractions of a second, atoms tear apart, nuclei split, and finally even subatomic particles rupture as space-time itself becomes unstable. This is speculative. We don't know if dark energy will strengthen. Current evidence suggests it might be constant, the cosmological constant scenario, which doesn't lead to the Big Rip. But we can't rule out other possibilities where dark energy grows over time. The Big Rip represents expansion taken to its ultimate extreme. Space stretching so violently that no force, no matter how strong, can hold anything together. Even the nuclear forces binding atoms would fail against the relentless acceleration. It's an apocalyptic vision, but also distant and uncertain. If it happens, it's tens of billions of years away. Long before then, the sun will have died, Earth incinerated or frozen, any descendants of humanity long departed or extinct. Still, the Big Rip reminds us that the universe's fate remains uncertain. Expansion might continue gently forever, or it might accelerate catastrophically, unmaking everything it once created, returning the cosmos to separated, isolated particles unable to interact across the vast, rapidly expanding distances between them. One of the most basic questions about the universe, does it have an edge, remains unanswered. We don't know if space is infinite, extending forever, or finite, eventually curving back on itself. Observations suggest the universe is geometrically flat, or very nearly so. In flat geometry, parallel lines never meet, triangles' angles sum to 180 degrees, and space likely extends infinitely. But observations only constrain the observable universe, the sphere from which light has had time to reach us. Beyond that, we simply don't know. The universe could be flat and infinite, or it could be flat locally, but have global topology that makes it finite, like the surface of a torus, which is locally flat but finite overall. If space is positively curved, like a sphere, it's finite. Travel far enough in any direction, and you'd eventually return to your starting point. The universe would have no edge, but also no infinity, just like Earth's surface has no edge but finite area. If space is negatively curved, hyperbolic, like a saddle, it's probably infinite, extending forever in all directions. Current measurements say the curvature is very close to zero, flat. But measurement uncertainty allows for slight positive or negative curvature, and even perfect flatness doesn't determine topology. A flat sheet extends infinitely, but a flat torus is finite. We might never know. If the universe is much larger than the observable region, we can't see its global structure. We're like ants on a vast sphere, unable to determine if the surface curves because we can only see a tiny patch. The universe might be infinite, filled with infinite galaxies, infinite stars, infinite possibilities. Or it might be finite, vast but bounded. Both are strange to contemplate. Theoretical physics has a problem. When quantum field theory calculates the vacuum energy, the energy of empty space, It predicts a value roughly 10^120 times larger than what we observe. This is called the cosmological constant problem, and it's spectacularly wrong. If vacuum energy were that large, the universe would have expanded so violently that no structures could form. Galaxies, stars, planets wouldn't exist. Yet here we are. Something must cancel almost all of this vacuum energy, leaving only the tiny remainder we observe as dark energy. But we don't know what or why. The cancellation must be precise to 120 decimal places, an extraordinary fine-tuning that suggests we're missing something fundamental. Maybe quantum field theory's calculation is wrong. Maybe vacuum energy doesn't contribute to the cosmological constant the way we think. Maybe there's new physics that naturally suppresses it. Or maybe the anthropic principle applies. In a multiverse with varying vacuum energies, only universes with values close to what we observe can support life. We exist in one of the rare, finely tuned universes because we couldn't exist anywhere else. But that feels unsatisfying to many physicists. It abandons the search for deeper explanation, accepting fine-tuning as selection bias rather than seeking underlying causes. The cosmological constant problem highlights how much we don't understand. Our best theories, quantum mechanics and general relativity, give wildly wrong answers when combined naively. We need new physics, new insights, perhaps a quantum theory of gravity to resolve this. Until then, it stands as physics' most embarrassing failure, a prediction so catastrophically wrong it suggests our understanding of vacuum energy, of space-time itself, remains profoundly incomplete. Why does time flow in one direction, past to future, never backward? Memory works one way, causes precede effects. Entropy increases. Yet most fundamental physics equations work equally well forward or backward in time. Newton's laws, Maxwell's electromagnetism, Schrödinger's equation, even general relativity, all are time symmetric. Run them backward, and you get valid physics. Yet we never see time reversal in everyday life. Broken eggs don't reassemble. Heat doesn't spontaneously flow from cold to hot. Movies played backward look absurd. The thermodynamic arrow of time, entropy increasing, explains much of this. Systems evolve toward higher entropy, greater disorder. This creates apparent time asymmetry. Low entropy states evolve toward high entropy, rarely the reverse. But why? The second law of thermodynamics says entropy increases in closed systems, but it's statistical, not absolute. Entropy could decrease. It's just overwhelmingly unlikely. And it doesn't explain why entropy was low initially. Why did the universe start in a low entropy state? This traces to the Big Bang. The early universe was extraordinarily smooth, uniform, low entropy. As it evolved, structure formed, galaxies, stars, complexity, which paradoxically represents higher entropy. The arrow of time emerges from this initial low entropy condition. But why did the universe begin with low entropy? We don't know. Perhaps it's explained by physics before the Big Bang, by boundary conditions we don't understand, by something in the nature of time itself. Other time arrows exist: cosmological, expansion direction, quantum, wave function collapse, psychological, subjective experience of time. Whether they're all related or independent remains unclear. Time's directionality feels fundamental, woven into our experience. Yet it emerges mysteriously from laws that don't inherently prefer forward over backward, from initial conditions we can't explain, from entropy's statistical tendency to increase. Throw a book into a black hole. Where does the information in that book go? The words, the molecular structure, the quantum states of every particle, all that information crosses the event horizon and seems lost forever. But quantum mechanics says information can't be destroyed. It might be scrambled, transformed, made unrecognizable, but the universe must preserve it somehow. Information conservation is fundamental to quantum theory. Yet general relativity says anything crossing a black hole's event horizon is gone, irretrievable. And Hawking radiation, the thermal radiation black holes emit, appears random, carrying no information about what fell in. If a black hole eventually evaporates completely, the information seems to vanish. This is the information paradox. Quantum mechanics and general relativity give contradictory answers. One of our most successful theories must be wrong or incomplete. Proposed solutions abound. Maybe information is encoded in Hawking radiation in subtle ways we don't yet understand. Maybe it's stored at the event horizon, smeared across the surface. Maybe information does escape, just incredibly slowly, in patterns too complex to recognize. Or perhaps the paradox reveals something profound, that black holes violate quantum mechanics in ways we haven't grasped, or that general relativity breaks down at horizons, or that information truly can be destroyed under extreme conditions. The paradox has driven decades of theoretical work in quantum gravity, string theory, holography. It's not just about black holes. It's about reconciling quantum mechanics with gravity, understanding what happens at reality's most extreme boundaries. Stephen Hawking famously bet that information was destroyed. Later, he conceded, admitting information probably escapes somehow, but exactly how remains unresolved. The information paradox represents a fundamental conflict between our best theories. Until we resolve it, we can't claim to truly understand black holes, quantum mechanics, or the deep nature of information itself. The universe keeps its secrets here, at the edge of understanding. What if particles aren't points, but strings, tiny vibrating loops of energy about 10 ma 35 meters long, oscillating in patterns that determine their properties? This is string theory's core idea. Different vibration patterns create different particles. A string vibrating one way is an electron, another way, a photon, another, a quark. All particles are fundamentally the same thing. Strings, just vibrating differently, like musical notes from a single instrument. But strings require extra dimensions to vibrate properly. Not just the 3 spatial dimensions we experience, but 10 or 11 total dimensions. The extra dimensions are compactified, curled up so tightly we don't perceive them, folded into shapes too small to see. The shape of these hidden dimensions determines physics. Different configurations produce different particles, different forces, different physical constants. Our universe's specific properties might reflect how these extra dimensions are folded. String theory elegantly unifies all forces, including gravity. It potentially resolves quantum gravity problems, explains particle properties, and connects everything through one framework. It's beautiful, mathematically sophisticated, perhaps the closest we've come to a theory of everything. But it has problems. It makes few testable predictions. The energy scales where strings manifest are far beyond any experiment we can perform. It predicts vast numbers of possible universes, the string landscape, making specific predictions difficult. And we have multiple versions, superstring theories, that might all be different aspects of a deeper theory we don't fully understand. Critics say string theory isn't science. It's unfalsifiable, more mathematics than physics. Supporters argue it's the only viable path toward quantum gravity, that we need patience as the theory develops. Regardless, string theory has transformed theoretical physics, offering glimpses of a universe far stranger than we imagined, one with hidden dimensions, where reality's fundamental constituents aren't particles, but vibrating strings, dancing in spaces we can't see. The universe is vast, billions of galaxies, each with billions of stars, many with planets. By simple statistics, intelligent life should exist elsewhere. Perhaps millions or billions of civilizations, yet we see no evidence, no signals, no visits, no artifacts. The silence is profound. This is the Fermi paradox, named after physicist Enrico Fermi's famous question: where is everybody? If life is common and even a small fraction develops technology, and civilizations expand even slowly into space, the galaxy should be teeming with life. They've had billions of years to spread. Earth should have been visited or colonized long ago, yet we seem alone. Explanations abound. Perhaps life is incredibly rare. Earth represents a unique confluence of factors. Perhaps intelligence rarely emerges, or civilizations inevitably destroy themselves before achieving interstellar travel. Perhaps they're there but hiding, avoiding contact. Perhaps interstellar travel is practically impossible, distances too vast, technology insufficient. Or perhaps we're early. The universe is young. Most stars capable of supporting life haven't formed yet. We might be among the first civilizations to arise. Or perhaps advanced civilizations transcend physical reality, uploading into virtual worlds, losing interest in expansion, becoming undetectable to beings like us, still bound to matter and planets. The paradox deepens with time. Every year we search and find nothing strengthens the mystery. SETI listens to the cosmos. Telescopes scan for megastructures. We find only silence. Maybe we're alone. Maybe intelligence is a cosmic fluke, arising once in a trillion planets. Or maybe we're surrounded by life, but too primitive to recognize the signs. Like bacteria trying to understand human civilization. The silence might be the universe's greatest mystery. Or we might be asking the wrong questions, looking in the wrong ways, not yet ready to see what's there. Some physicists and philosophers propose that consciousness plays a role in quantum mechanics, that observation causing wave function collapse requires conscious awareness. It's controversial, speculative, and deeply intriguing. The measurement problem asks what counts as observation. Does a detector suffice? Or does someone need to read the detector? If consciousness is required, quantum mechanics becomes intimately tied to mind, awareness, subjective experience. The Copenhagen interpretation in some readings suggests observation is special, that conscious measurement collapses superposition. Without consciousness, the universe exists in undetermined states. Mind creates reality, in a sense. Others propose quantum mechanics in the brain might explain consciousness. Roger Penrose and Stuart Hameroff suggest quantum processes in cellular structures called microtubules generate consciousness. It's speculative, lacking strong evidence, but intriguing. Most physicists reject consciousness collapse ideas. Decoherence explains wave function collapse without invoking awareness. Detectors, environments, interactions, these suffice without consciousness, but questions linger. Consciousness is deeply mysterious. We don't understand how subjective experience emerges from physical processes. And quantum mechanics is strange. Measurement seems special, different from mere interaction. Some wonder if these mysteries connect. Perhaps consciousness is what it's like to be a quantum system maintaining coherence. Perhaps awareness is entanglement from the inside. Perhaps our subjective sense of choice reflects genuine quantum indeterminacy. Or perhaps consciousness and quantum mechanics are unrelated, two mysteries that happen to coexist but don't illuminate each other. Our minds grasp for patterns, seeking connections where none exist. The truth is, we don't know. Consciousness remains unexplained. Quantum mechanics remains interpretatively uncertain. Linking them is tempting but unproven. It might be profound insight or wishful thinking. For now, the connection, if any, remains in the realm of speculation, possibility, and wonder. Quantum field theory predicts empty space should seethe with energy. Virtual particles, quantum fluctuations, fields in their ground states. Calculate this vacuum energy density, and you get an enormous number, roughly 10⁻13 joules per cubic meter. But observations show vacuum energy is nearly zero, or more precisely, it's the tiny positive value we associate with dark energy, about 10⁻9 joules per cubic meter. The discrepancy is staggering, 120 orders of magnitude. Predicted versus observed, it's the worst prediction in physics. We call it the vacuum catastrophe. If vacuum energy were as large as predicted, its gravitational effect would dominate everything. The universe would have expanded so violently that no structures could form, or it would have collapsed immediately. Reality as we know it couldn't exist. Something must cancel almost all the predicted vacuum energy, leaving only the tiny remainder we observe. But what? And why so precisely? Perhaps our calculation is wrong. Maybe vacuum energy doesn't contribute to gravity the way we think. Perhaps new physics at high energies cancels contributions we're calculating. Perhaps supersymmetry, a hypothetical symmetry between particles, provides cancellation, though we haven't observed supersymmetry experimentally. Or perhaps the anthropic principle applies. In a multiverse with varying vacuum energies, only universes with values near zero support structure, life, observers. We exist in one of the rare fine-tuned universes because we couldn't exist elsewhere. The vacuum catastrophe connects to the cosmological constant problem. They're aspects of the same mystery. Why is vacuum energy so small? The question touches quantum mechanics, general relativity, cosmology, maybe even the nature of existence itself. We don't have answers. We have a spectacular discrepancy, a puzzle pointing toward physics beyond our current understanding, perhaps requiring quantum gravity or radical new insights about the nature of space, energy, and the vacuum's true character. In 2012, Nobel laureate Frank Wilczek proposed something strange: time crystals, structures that repeat in time the way ordinary crystals repeat in space, oscillating perpetually without consuming energy. Normal crystals have atoms arranged in repeating spatial patterns. Time crystals would have states that repeat in temporal patterns, cycling through configurations periodically without external driving. This sounds like perpetual motion, which thermodynamics forbids. But time crystals exist in quantum systems away from equilibrium, skirting traditional thermodynamic restrictions. They're not closed systems in equilibrium. They're open, driven systems that nonetheless exhibit persistent oscillation. In 2017, physicists created time crystals experimentally, chains of ions hit with laser pulses, creating systems that oscillated at twice the driving frequency. The systems maintained this rhythm indefinitely without settling into equilibrium, defying expectations. Time crystals represent a new phase of matter, joining solids, liquids, gases, plasmas, and other exotic states. They challenge our understanding of equilibrium, symmetry, and thermodynamics. Why do they matter? They might help quantum computers maintain coherence longer, storing information in states that naturally resist settling. They represent fundamental physics we didn't expect, new possibilities for how matter behaves. Time crystals blur boundaries. They're not static but not conventionally dynamic. They repeat but don't require energy input for repetition. They're ordered in time, not just space. Perhaps they hint at deeper principles, symmetries we haven't recognized, phases of matter we haven't imagined. The universe permits structures that oscillate eternally, crystallizing not just in space but in time itself, finding order in temporal patterns that resist decay. It's early days for time crystals. We're still understanding their properties, limitations, potential applications. But they've expanded the catalog of possible matter, revealing that the universe contains more variety, more strangeness than we thought. The strong nuclear force, which holds quarks together in protons and neutrons, could violate a symmetry called CP, the combination of charge, conjugation, and parity. Theory allows this violation. Experiments show it doesn't happen, or happens at levels far below what theory permits. This is the strong CP problem. Why does nature choose not to violate CP in strong interactions when nothing forbids it? CP violation means physics treats particles differently from their antimatter mirror images. We observe this in weak nuclear interactions. Certain particle decays prefer matter over antimatter, but the strong force shows no such preference, despite having parameters in its equations that would permit CP violation. One parameter, the theta parameter, could range from 0 to 2p, but experimentally, it's less than 10 tau 10. Why so close to 0? Theoretical values suggest it should be order 1. The fine-tuning is extraordinary. Proposed solutions include the Pizzi-Quinn mechanism, which introduces new particles called axions that dynamically drive theta toward 0. Axions, if they exist, might also be dark matter candidates, potentially solving two problems simultaneously. But we haven't detected axions. The strong CP problem remains unresolved. It represents another fine-tuning puzzle. Nature makes a choice, theta near 0, that seems arbitrary, unexplained by known principles. Perhaps deeper physics determines this value. Perhaps symmetries we don't understand enforce it. Or perhaps, like other fine-tuning problems, it's anthropic. Only universes with theta near 0 permit stable matter and observers. We exist in one such universe because we couldn't exist elsewhere. The strong CP problem reminds us how many mysteries remain even in well-established theories. The strong force is part of the Standard Model, our most successful theory of particles. Yet we don't understand why it behaves as gently as it does, why it respects symmetries it could violate. Gravity is absurdly weak compared to other fundamental forces, about 1036 times weaker than electromagnetism. You can lift a paperclip with a tiny magnet, overcoming Earth's entire gravitational pull. Why this enormous disparity? This is the hierarchy problem. The weakness of gravity, or equivalently, the lightness of the Higgs boson mass, seems unnatural, requiring extreme fine-tuning to maintain across quantum corrections. In quantum field theory, virtual particles create corrections to masses and forces. For the Higgs, these corrections should be enormous, driving its mass up to the Planck scale, about 10^19 times larger than observed. Yet somehow corrections cancel almost perfectly, leaving the Higgs light. This cancellation requires fine-tuning to about 1 part in 1032. Change parameters slightly and the Higgs becomes impossibly heavy. Electroweak symmetry breaking fails, and atoms can't exist. Proposed solutions abound. Supersymmetry introduces partner particles whose contributions cancel precisely, naturally explaining the hierarchy. Extra dimensions might dilute gravity, spreading it into hidden dimensions and making it appear weaker in our 3 spatial dimensions. But we haven't observed supersymmetry or extra dimensions. The Large Hadron Collider searches for new physics that would explain the hierarchy, but finds only standard model particles. The hierarchy remains unexplained. Perhaps we're asking the wrong question. Perhaps the hierarchy isn't unnatural, but anthropic. Only universes with weak gravity support complex structures, stars, life. We observed this hierarchy because we couldn't exist without it. Or perhaps new physics awaits discovery just beyond current experimental reach, explaining naturally why gravity is so weak, why the Higgs is so light. The hierarchy problem touches the foundations of particle physics, cosmology, perhaps quantum gravity. It's a crack in the standard model, a place where our best theories seem incomplete, suggesting deeper principles waiting to be uncovered. Physics has 2 incredibly successful theories. General relativity describes gravity, space-time, the cosmos. Quantum mechanics describes particles, atoms, the microscopic world. Both work brilliantly in their domains, but they contradict each other fundamentally, and we can't unite them. At the Planck scale, 1035 meters, 1043 seconds, both quantum effects and gravitational effects become important. Space-time itself should fluctuate quantum mechanically. But general relativity treats space-time as smooth, continuous. Quantum mechanics treats particles and forces as discrete, probabilistic. Combine them naively, and you get nonsense. Infinities, contradictions, equations that can't be solved. We lack a theory of quantum gravity. This isn't just academic. Black hole singularities, the Big Bang, the universe's earliest moments. These require quantum gravity to understand. Without it, our knowledge hits walls, places where physics breaks down, and we can't predict what happens. String theory offers one approach, replacing point particles with vibrating strings, incorporating gravity naturally. Loop quantum gravity offers another, quantizing space-time itself into discrete units. Other approaches exist: causal dynamical triangulations, asymptotic safety, emergent gravity. But none are proven. We lack experimental guidance. The energies where quantum gravity manifests are far beyond any accelerator we can build. We must rely on mathematics, consistency, indirect evidence, cosmic observations, black hole physics, gravitational waves. The lack of quantum gravity represents physics' deepest incompleteness. Our 2 foundational theories, both verified to extraordinary precision, can't coexist. One or both must be modified, extended, perhaps radically reimagined. Solving quantum gravity might reveal space-time's true nature. Perhaps it's emergent from something more fundamental, perhaps information or entanglement. Perhaps space and time aren't real, but convenient descriptions of deeper quantum processes. Until we solve it, we can't claim to understand reality's foundations. The universe keeps its deepest secrets here. Perhaps our universe isn't alone. Perhaps it's one bubble in an infinite cosmic foam, a multiverse where every possible variation of physical laws, constants, and initial conditions exists somewhere. String theory suggests this. Its equations have countless solutions, perhaps 10,500 or more, each representing a different possible universe with different particles, forces, constants. Our universe occupies one solution. Others exist elsewhere. Eternal inflation suggests this too. If inflation, the rapid expansion in the universe's earliest moments, is eternal, it creates infinite bubble universes, each potentially with different physics, separated by eternally inflating space. In this multiverse, every possible universe exists. Some have no stars, gravity too weak or too strong. Some have no chemistry, electromagnetic forces wrong. Some last nanoseconds, others trillion of years. Some support complexity, structure, life. Most don't. We inhabit a rare bubble where physics permits observers. Not because it's special objectively, but because we couldn't exist elsewhere. The anthropic principle becomes explanatory. Fine-tuning isn't miraculous, but selection bias across infinite possibilities. This is controversial. Critics say it's unfalsifiable, unscientific. If anything is possible somewhere, the multiverse explains nothing, predicts nothing. It gives up on understanding why our universe has the properties it does. Supporters argue it's the natural consequence of our best theories, that we shouldn't ignore where physics leads. And perhaps some multiverse versions are testable, through cosmic microwave background patterns, through gravitational waves from bubble collisions. If true, reality is vaster than we imagined. Our universe, all 93 billion light-years of observable space, all its galaxies and stars, is one note in an eternal symphony, one universe among infinite, variations most unlike our own, stretching beyond imagination through dimensions of possibility we're only beginning to contemplate. And perhaps that's a fitting place to end, with mystery, with vastness, with the recognition that after all our discoveries, the universe remains far stranger and larger than we can fully comprehend. And so we arrive at the end of our journey through physics, through 100 facts about the universe, from the smallest quantum fluctuations to the grandest cosmic structures, from the concrete to the speculative, from what we know to what we wonder. If you're still awake, and it's perfectly fine if you're not, perhaps you're feeling that particular vertigo that comes from contemplating the universe's true strangeness. The way solid matter is mostly empty space. The way time flows differently, depending on where you are and how fast you're moving. The way reality, at its deepest levels, refuses to fit into the neat categories we've built for it. Physics is humanity's patient conversation with nature, stretching back millennia and continuing into an open future. We've learned so much, enough to build technologies that would seem like magic to our ancestors, enough to peer back nearly to the universe's beginning, enough to manipulate matter at atomic scales and detect gravitational waves from colliding black holes a billion light years away. And yet, for all we've learned, mystery remains. Dark matter and dark energy comprise 95% of the universe, and we don't know what they are. We can't reconcile quantum mechanics with gravity. We don't understand consciousness, or why time flows forward, or whether the universe is finite or infinite. Perhaps that's as it should be. A universe fully understood might be less wondrous than one that still holds secrets. The questions that remain, the puzzles that resist our best efforts, keep us curious, keep us searching, keep us humble before the vastness and complexity of existence. Sleep well if sleep finds you, and know that the universe continues its patient work. Atoms assembling and disassembling, photons crossing cosmic distances, quantum fields fluctuating in the vacuum, time flowing forward for reasons we still don't fully understand. You're part of it all, stardust contemplating stardust, the universe observing itself through temporary configurations of matter that happen for a brief time to be conscious. Good night, and thank you for wondering with me.